Hello there and welcome to Physics with William, where curiosity settles in for the evening and even the smallest corners of the universe are allowed to take their time. Tonight, I would like to bring you somewhere very small indeed. Not merely small in the way a grain of sand is small beside a beach, or a pebble is small beside a mountain, but small in the way that makes ordinary words feel a little clumsy. We're going to the centre of the atom, to that compact and stubborn little region called the nucleus, a place so tiny that if atoms were the size of great cathedrals, the nucleus would still be little more than a speck hidden deep within the stonework. And yet almost all the mass is there, packed into a space so cramped and intense that the mind does not accept it immediately. It sounds less like physics, and more like someone trying to store an elephant in a biscuit tin. Before we ease into that strange and crowded heart of matter, I would love to ask you something simple. Where in the world are you listening from tonight, and what sort of hour has found you there? Is it late and quiet with the rest of the house beginning to settle into stillness? Is it early with the day only just loosening its grip? Are you under rain, city light, open countryside, or the dim little glow of a bedside lamp that makes everything feel briefly manageable? It is always a lovely thought that a conversation about the hidden centre of atoms can drift across so many places at once, arriving in kitchens, bedrooms, trains, desks, and sleepless corners of the world. And if you find this gentle journey soothing, or interesting, or simply a pleasant way to let the mind wander without too much effort, then do give the video a like, and perhaps subscribe as well. It helps this calm little corner of science find other people who might enjoy an evening spent with difficult questions and patient answers. Not that I would ever want to keep you awake with nuclear physics, though if that does happen, at least you will be unusually well informed for someone staring at the ceiling in the dark. Now then, let us begin with an odd fact, because the nucleus is full of those. Every object around you, every chair, spoon, blanket, wall, cloud, cat, kettle, and cup of tea is made of atoms. That much we say quite easily now, as if it has always been obvious. But each atom, despite sounding complete and self-contained, is mostly empty space. There is a centre, yes, and around that centre there are electrons, but the atom itself is not a little solid bead. It is a structured thing, airy in some ways, concentrated in others, with almost everything that counts gathered into a tiny middle. If the atom were stretched to the size of a football stadium, the nucleus would be more like a pea or a small bead somewhere near the centre, while the electrons would belong to the spacious outer reaches. That picture alone is strange enough to deserve a moment. Matter feels solid. Your hand on a table does not report emptiness. Your feet on the floor do not suggest a grand architecture of vacant room. And yet here we are, living among objects made mostly of space, anchored by cores so small and so dense that they sound invented. The nucleus is one of those things we grow used to hearing about long before we really stop to consider how peculiar it is. The word becomes familiar in school, in documentaries, in diagrams with tidy circles and coloured dots. It starts to sound normal. But the moment you slow down and ask what it actually is, not just what we call it, the whole subject becomes wonderfully awkward again. What is this tiny centre? Why is it there? What is packed into it? Why does it hold together? Why does it sometimes change, split, or throw pieces of itself out into the world? And perhaps most intriguingly, why does it remain intact at all when by all ordinary reasoning it ought to push itself apart? That last question is the one that makes the nucleus especially delightful, because it gives the subject a kind of built-in tension. The nucleus is made partly of protons, and protons carry positive electric charge. Positive charge does not like company of its own kind. It repels. One proton pushes another away. Two of them want distance. A whole bunch of them crowded into the same microscopic region ought to be a recipe for complete bad temper. The larger the nucleus, the more dramatic that problem becomes. It is as though nature gathered a room full of people who all insist on standing apart, then shut the door and somehow persuaded them not only to stay, but to remain packed shoulder to shoulder in the smallest room imaginable. Something very powerful must be going on in there, because by the logic of electricity alone the whole thing should come undone at once. And this is where the atomic nucleus stops being merely small and starts becoming truly dramatic. Hidden inside ordinary matter is a constant negotiation between things that attract and things that repel, between confinement and escape, between stability and the ever-present possibility of change. A nucleus is not just a dot at the middle of a textbook drawing. It is a packed arrangement of particles held together under conditions that would seem absurd if written in any other context. It is a quiet little object with an outrageous internal life. Perhaps this is one reason the nucleus has fascinated physicists for so long. It takes the familiar and makes it strange. We all know what ordinary objects do. They sit on shelves, gather dust, chip at the edges, warm in sunlight, cool on windowsills. But beneath that everyday behaviour lies a deeper level of organisation that is anything but ordinary. In the centre of the atoms making up your body, the air and the ground beneath you, are millions upon zillions of these compact cores, each one built from particles crammed together so tightly that they barely seem to have room to exist, and each one governed by rules that do not feel borrowed from daily life at all. There is also something pleasingly humbling in that idea. The world looks calm. A stone sits quietly in a field and appears to be the very model of stillness, and yet inside the atoms of that stone are nuclei assembled by forces of astonishing strength. Their histories reaching back to stars, collisions and ancient events long before that stone ever became a stone. It is one of the recurring lessons of physics that the quietest things are often the busiest when examined closely enough. A wall can be full of motion, a vacuum can be full of possibility. A tiny central core can carry nearly all the mass of an atom and enough tension to make the phrase holding it together sound almost heroic. If you were encountering the idea of the nucleus for the first time, you might guess that it had always been obvious. After all, once we know atoms exist, surely it is only a short stroll to discovering their centre. But the real path was much less tidy. People once imagined atoms as indivisible little units, solid and complete. Then came the realization that atoms were themselves structured. Electrons were found. New models appeared. Suddenly the atom was no longer the final building block, but a thing with parts, and once that door opened, physics had no choice but to keep walking through. The nucleus did not arrive as a cosy finishing touch. It arrived because experiments began to show that the atom had a concentrated core, a central region holding most of its mass and positive charge. That discovery changed everything, not only because it altered the shape of the atom in scientific thinking, but because it revealed just how much energy, complexity and hidden architecture could fit inside something once assumed simple. And even now, with all the diagrams and all the years of study behind us, the nucleus remains a difficult thing to picture honestly. It is tempting to imagine it as a neat bundle of little spheres pressed together like marbles in a box. That picture is not entirely useless, but it can be misleadingly comfortable. The nucleus is not a miniature pile of peas, it is a quantum object, a system whose internal behaviour is shaped by rules that do not resemble the ordinary mechanics of billiard balls and stacked fruit. Its ingredients are real enough, but their arrangement is not the sort of arrangement your intuition was trained for by living among chairs and shoes and spoons. That is part of why this subject can feel slippery at first. The nucleus is concrete in the sense that it has measurable properties, real effects and genuine structure, but the way it exists is stranger than the mind prefers on a sleepy evening. Still, there is great value in staying with the strangeness rather than rushing past it, because once you do, the nucleus begins to feel less like a forbidding topic and more like a remarkable answer to a very old puzzle. What is matter really made of? What gives atoms their mass? Why do some elements remain stable for immense spans of time while others decay, split or transform? Why can tiny changes in the nucleus release energies so immense that human history itself has been reshaped by learning how to tap them. These are not side questions. They lead directly to stars, to radioactivity, to medical imaging, to the heat inside Earth, to the origin of the elements, and to some of the most consequential scientific discoveries ever made. But tonight, at least for now, we begin more gently. Not with a rush into all the details, but with the simple invitation to look again at the atom and notice what has been hiding in plain sight. There is a little centre there, tiny beyond ordinary comparison, dense beyond common sense, full of positive charge that by simple reasoning should erupt outward. And yet it does not. It stays, it endures, it governs the character of the element it belongs to. It helps determine what kind of matter something is, how heavy it is, how stable it may be, and what transformations it can undergo. The nucleus sits quietly beneath the visible world like a secret engine. There is something almost comical in the scale mismatch involved. We spend our lives dealing with large visible things, furniture, buildings, landscapes, weather, traffic, laundry, which has its own laws and rarely seems to conserve socks. But the deeper structure of all of it depends on something so small that any attempt to compare it to household objects begins to feel ridiculous. The nucleus is not merely beyond sight. It is beyond the scale where sight feels relevant. No eye evolved to understand such a place. No ancestral survival problem required our species to picture tightly bound collections of protons and neutrons hidden inside atoms. We had to invent the conceptual tools for it. We had to learn how to infer the invisible from traces, measurements, scattering patterns, and mathematical descriptions. The nucleus is one of those triumphs of human thought where we did not find the answer by looking directly, but by asking nature careful questions and taking her indirect replies very seriously. And what nature replied, in essence, was this: matter has a centre. The centre is crowded. The crowd includes positively charged particles that ought to repel one another strongly. There are also neutrons, which carry no electric charge but matter a great deal. The whole assembly is held together by an interaction so strong at short range that it can overpower the electric repulsion, at least within the tiny confines of the nucleus. Yet that grip has limits. It does not reach far. It does not make every arrangement stable. In some nuclei, the balance works beautifully. In others, it barely works at all. In the heaviest and most delicate cases, the tension becomes too much, and change begins. A nucleus may spit out a fragment, transform a particle, or divide. So even before we study the details, we already glimpse the basic drama. The nucleus is a crowded compromise between opposing tendencies. You can almost think of it as a neighbourhood dispute taking place under impossible conditions. The protons all object to one another on electrical grounds. The strong nuclear interaction arrives and says, in effect, everyone stay close and stop making a scene. The neutrons help, not by solving every problem, but by adding binding without adding electric repulsion. For a while, this arrangement can produce excellent order, but if too many protons gather, or the balance between ingredients slips too far, the piece becomes fragile. The nucleus then reveals that stability is not a default state. It is an achievement. That is one of the ideas worth carrying with you as we move deeper into this subject. Stability in physics is often something that must be explained, not assumed. When you first hear about a rock or a table, stability feels boringly obvious. Of course it sits there. What else would it do? But the more microscopic the level, the less natural stillness becomes. At the atomic scale, at the nuclear scale, what seems quiet from the outside may depend on an exact balance of competing effects. A nucleus is not stable because nature always prefers peace and tidiness. A nucleus is stable when the underlying rules permit a certain arrangement to hold together better than the available alternatives. That can be true for a very long time, or not. This is also why the phrase atomic nucleus carries more weight than it first appears to. It is not merely the middle of the atom in the geometric sense. It is the central repository of the atom's identity. Change the number of protons and you change the element itself. Add or remove neutrons and you may change its stability, its mass, the way it behaves in nuclear processes, or whether it quietly persists or gradually transforms. The electrons govern chemistry in many familiar ways, but the nucleus sets the deeper badge of identity. It is the administrative office of the atom, the archive, the vault, and occasionally the source of spectacular paperwork errors. And perhaps that is where the wonder of the subject lies for me. The nucleus is so small that it would be easy to dismiss it as merely a technical detail in the larger story of matter. But it is not a detail. It is a concentrated account of some of the biggest themes in all of physics. Structure hidden within apparent simplicity, powerful forces operating where intuition fails, stability emerging from tension, enormous consequences arising from tiny scales, the elements forged in stars, the energy in the sun, the radioactivity in rocks, the medical traces in hospitals, the terrible and transformative power of nuclear weapons. All of these roads pass through the nucleus. For now, though, we do not need to sprint ahead. It is enough to settle into the first puzzle and let it become vivid. At the centre of every atom is a compact bundle containing positive charge. Positive charge repels positive charge. By that reasoning alone, the nucleus should not last. It should burst apart. And yet the world around us remains full of atoms whose nuclei hold together quite well. Tables do not dissolve into sprays of protons. Teacups do not disintegrate in moments of emotional distress. Mountains do not abruptly reconsider their internal arrangements. Something deep in nature is enforcing a strange and powerful order, keeping these tiny centres bound despite the odds. That is the quiet question we will keep near us as we continue. What is a nucleus really? Once we stop treating it as a dot in a diagram, what lives inside it? What holds it together? Why does that grip work so powerfully at short range and yet fail in certain cases? How can so much energy be tied up in such a small place? And what does it mean that the everyday world rests on the success of countless microscopic structures that always seem to be one principle away from flying apart? So get comfortable. Let the room soften a little around you and keep that image in mind. Not the neat cartoon version, but the real one as far as we can manage it. A tiny core hidden in every atom. Dense, crowded, electrically unruly, and somehow still bound. It is one of the universe's most elegant acts of restraint, and the closer we look, the stranger and more impressive it becomes. In a moment the picture sharpens, because to understand why that centre exists at all, we have to go back to the time when no one knew it was there, and when the atom itself still seemed far simpler than it really was. For most of human history, the atom was not a place anyone expected to have an interior. It was supposed to be the end of the line, the smallest unit, the final grain beyond which matter could not be divided any further. The very idea carried that meaning. An atom was thought of as something cut no more, something complete in itself, solid in the way a pebble seems solid when you do not own a hammer. That made it tidy, satisfying, and wrong in the way many early ideas are wrong. Not foolishly wrong, not carelessly wrong, but wrong in a way that reveals how the mind prefers simple endings. We like to imagine that the search eventually reaches a last brick. Nature, rather annoyingly and very consistently, has other habits. Even after scientists became more confident that atoms were real, and not merely convenient ideas for doing chemistry, the picture remained vague for a long time. People could infer their existence from the way substances combined, from gases, from reactions, from the numerical regularities that chemistry kept presenting like a stern schoolmaster. But inference is not the same as vision. No one could look down into the atom and report its layout. No one could stroll up to it, knock politely and ask whether it had rooms. The atom sat beyond the reach of ordinary senses, and so it lived first in the imagination as a kind of necessary unit. Very useful, clearly real in some practical sense, but hidden. That hiddenness matters, because it shaped how discovery unfolded. The nucleus was not found by direct inspection. It had to be cornered by evidence. It had to be exposed by asking the atom questions in ways that forced it to answer indirectly. This is one of the most impressive habits of physics. When nature refuses to show herself plainly, physics arranges little traps. It measures deflections, tracks energies, records flashes, and notices patterns in what bounces, what passes through, and what changes direction. The invisible then begins to leave fingerprints. Enough fingerprints, and the suspect can no longer claim innocence. Before the nucleus entered the story, the atom already had one surprise hidden inside it. That surprise was the electron. Once electrons were discovered, the old idea of the atom as a featureless solid unit could no longer survive. Something smaller was part of the atom. Something with negative electric charge existed inside a structure once assumed indivisible. That was a major shift, and it forced scientists to invent new pictures of what an atom might be. One of the most famous was the model proposed by Joseph John Thomson, the same physicist closely associated with the discovery of the electron. In his picture, the atom was a kind of diffuse positive substance with negatively charged electrons embedded within it. This picture is often remembered through a domestic dessert comparison, which has the advantage of being memorable and the disadvantage of making the atom sound more comforting than it really was. The basic idea, though, was simple enough. If electrons carried negative charge, there had to be positive charge somewhere to balance things out, because ordinary atoms are electrically neutral overall. Thomson imagined that positive charge was spread through the atom rather than concentrated in one tiny place. The electrons sat inside that spread out positive background. It was a reasonable step at the time. It acknowledged internal structure without yet demanding a violent rearrangement of atomic thinking. And it is worth being fair to these earlier models because hindsight can make the past look silly when it was nothing of the kind. Scientists were not blundering about in comic ignorance. They were working with limited evidence and trying to build the best picture available. A model does not have to be perfect to be useful. It only has to survive until a better one appears. In science, even an incorrect picture can be a valuable bridge if it organises known facts and points the way towards sharper tests. The trouble for Thomson's atom was not that it was laughable. The trouble was that nature had a much more concentrated secret in mind. To understand how that secret was revealed, it helps to appreciate the peculiar challenge involved. If atoms are overwhelmingly tiny, then any internal feature within them is even more difficult to detect. You're not merely trying to study something small, you're trying to study structure inside something small. It is like being told there is a specific grain of sand on a beach, and then being told that grain of sand may itself contain a hidden city. A great many things could be imagined, but the question is how to test them. The answer came from scattering experiments, which sound modest and are in fact among the most revealing tools in all of physics. If you cannot see inside something, you can throw something at it and watch what happens. Not in a clumsy or destructive sense, though clumsy destruction does have its uses elsewhere, but in a careful probing sense. The way incoming particles pass through a target, slow down or change direction, can reveal what sort of electric fields and material structures lie inside. It is a bit like learning the layout of a dark room by rolling marbles through it and listening for where they bounce. With enough patience and precision, the marbles start telling stories. The experiment most closely linked with the discovery of the nucleus is associated with Ernest Rutherford and with the work of Hans Geiger and Ernest Marsden. Thin metal foil, famously gold, was used as a target. Very small positively charged particles were directed toward it. The expectation under the diffuse atom picture was fairly mild. If positive charge was spread out through the atom, then those incoming particles should mostly pass through with only small deflections. A few slight nudges here and there perhaps, but nothing dramatic. It would be like firing tiny projectiles through a region filled with very gentle electric influence. The atom, in that case, would not offer a sharply localized obstacle. Most of the particles did in fact pass through. That part was not shocking. Atoms are mostly empty space in the structural sense. and thin foil leaves lots of room for particles to thread their way through. But every now and then, something astonishing happened. A small number of the incoming particles were deflected through very large angles. A few even appeared to bounce almost straight back. That result was extraordinary. It meant that somewhere inside the atom, there had to be a region of very concentrated positive charge and mass, something compact enough and intense enough to produce such strong deflections when approached closely. Rutherford later described his surprise with a comparison that has become famous. It was, he said in essence, as startling as if one fired a projectile at tissue paper and it came back. The force of that image still works because it captures the mismatch between expectation and result. If the atom was soft and diffuse in the relevant electrical sense, there was no reason for such dramatic rebounds. Those sharp reversals implied that the incoming particles had sometimes come very near a tiny, dense, positively charged centre. Not a spread-out haze, not a gentle pudding of charge, a centre. That was the beginning of the modern nuclear picture. The atom, it turned out, was not a loose cloud of positivity with electrons tucked into it like bits in a bun. It had a compact central region carrying positive charge and most of the mass. Around that centre, electrons occupied the broader atomic domain. Suddenly, the atom became a place with a middle, and a vast amount of apparent emptiness around that middle. Matter had opened up internally. The familiar world was built from things that were structured more like miniature systems than solid beads. The phrase "no one could see" fits this stage of the story rather well, because the nucleus was never visible in the ordinary sense. It was unavoidable, which is not the same thing. Scientists did not discover it by peering through a sufficiently heroic microscope and finally spotting a tiny glowing dot. They discovered it because the old atomic model stopped making sense of what particles were doing. The nucleus announced itself by the way it disrupted an experiment. That is often how deep discoveries arrive, not as a warm introduction, but as a refusal of the previous story. There is something deeply satisfying about that sort of discovery because it depends less on human preference than on consistency. You may like one picture of the world better than another. You may find one model elegant and another awkward. Nature does not especially care. If the particles come back in directions they should not under your model is in trouble. The nucleus forced its way into science because it accounted for the evidence better than the alternatives. It was not adopted because it was charming. It was adopted because the atom had betrayed its centre. And once that centre was accepted, a great many things had to be reconsidered. The atom was not a smooth distribution of positive charge after all. Positive charge was concentrated into a very small region. That immediately raised new questions. How small was that region? How much of the atom's mass sat there? What was it made of? How did electrons behave in relation to it? And perhaps most importantly, how could such a compact positive core exist without tearing itself apart? That last question did not arrive all at once in full force, but it was lurking in the shadows from the moment positive charge became confined to a tiny centre. It is also worth noticing how unusual the discovery was in emotional terms. Many scientific ideas become less strange as they become more accurate. The nucleus did not. In some ways, it made matter far stranger than before. A solid object now had to be understood as mostly spatial rooms structured around tiny dense centres. The mass of the atom was packed into a central region incredibly small compared with the atom as a whole. Positive charge, which one might have preferred to imagine as politely spread out, was crowded into the middle. The atom became less like a ball and more like a vast arrangement focused on a minute and heavy heart. There is nothing in ordinary daily experience that prepares us for that naturally. No loaf of bread conceals most of its substance in a pinpoint. No room stores all its furniture in the centre, while the walls merely suggest a boundary of influence. Atomic structure had wandered far from common sense. From there, the story only grew more interesting. Rutherford's early picture gave the atom its centre, but the nucleus itself was not yet fully understood. At first, one might have imagined it as a cluster of positive charges somehow accounting for atomic mass. Yet as investigations continued, it became clear that the nucleus had its own internal complexity. there was another particle to be reckoned with, one carrying no electric charge, but contributing substantially to nuclear mass and stability. That particle, the neutron, would prove essential. Without it, the nucleus would remain a deeply incomplete idea, a kind of half-solved riddle. But even before the neutron was identified, the basic revelation had already landed. The atom had a tiny central core, and that core mattered enormously. Think for a moment about how radical that really was. Chemistry had already taught scientists that elements differ by their atomic nature. Physics was now saying that the identity of the atom depended crucially on a tiny centre carrying positive charge. This meant that the deep character of matter was tied to something hidden at almost impossible scale, something whose arrangement determined not just mass distribution, but the very kind of atom under discussion. A change in the central positive count would not be a cosmetic adjustment. It would mean a different element altogether. The centre was no longer merely a curiosity. It was the anchor of identity. And still, nobody could see it in the ordinary sense. That remained true throughout all the refinements. What changed was not human eyesight, but the sophistication of our questions. We learned to use one part of nature to probe another. We learned to make sources of particles, to detect scattering patterns, to infer size and charge concentration from behaviour. Later generations would add even more refined tools, more energetic probes, more powerful detectors, and more elaborate theoretical frameworks. Yet the underlying achievement stayed the same in spirit. The nucleus became known because the world around it would not behave as though it were absent. That is one reason the history of atomic structure can be so pleasing to revisit. It reminds us that science often advances by disciplined discomfort. A model works well enough until one experiment refuses to cooperate. Then the scientist has a choice: protect the old picture with excuses, or follow the evidence into stranger territory. The nucleus belongs to that second path. It was a stranger truth accepted because the old comfort no longer held. You can almost picture the intellectual mood of the time. First there is satisfaction at having atoms and electrons in the story at all. Then comes the realization that the atom must be neutral overall, so some positive component must exist. A diffuse picture seems adequate. Then the scattering results arrive and ruin the easy arrangement. Suddenly most of the atom appears empty in one sense, while its mass and positive charge occupy a concentrated centre. The polite architecture collapses. The atom becomes both simpler and more dramatic at once. Simpler because it has a clear centre, more dramatic because that centre is unbelievably dense and charged. There is another subtle point here that matters for everything that follows. The nucleus was not discovered as a decorative feature of matter. It emerged because matter had to contain a concentrated source of influence strong enough to redirect incoming charge particles sharply. That means the nucleus entered physics already wearing the clothes of force and concentration. From the first, it was associated with strong electric effects at close range and with a packing of mass that dwarfed expectations. It was never going to remain a quiet bookkeeping detail. Once found, it practically demanded a new branch of questions, and those questions became unavoidable. If positive charge lived in a tiny central volume, then the particles carrying that charge must be very close together. How close? Close enough that their mutual electrical repulsion should matter greatly. That is not a tiny technical footnote. It is a structural crisis waiting to be explained. A few positively charged particles near one another are manageable enough as a concept, but a central region containing several or many such charges in extreme proximity immediately raises the problem that will define the next stage of our journey. Why does that centre hold together? The answer was not available at once, and perhaps that is what makes this stretch of the story so human. Discovery does not always arrive fully dressed and carrying its own explanations. Often one revelation creates a dozen new mysteries. The nucleus was one of those revelations. It solved the scattering puzzle by giving the atom a tiny centre. It did not yet explain the internal peace treaty of that centre. It did not yet tell us all its ingredients. It did not yet reveal the force powerful enough to outweigh electrical repulsion at short range. It simply made the existence of such a force unavoidable. So when we say the tiny centre no one could see, we are really speaking about more than a historical moment. We are speaking about a change in how the invisible became thinkable. The nucleus is a triumph of indirect knowledge. It was not plucked from plain sight. It was extracted from consequences. It was deduced because particles behaved as though a concentrated centre existed, and nothing softer or more spread out could explain them as well. From that point onward, the atom was no longer a simple container of charge. It was a spacious structure built around a central knot of extraordinary significance. Once that knot had been revealed, the old calm description of the atom could never fully return. The centre was too small, too dense, too charged, too consequential. It demanded attention. It invited questions not just about atomic structure, but about the very possibility of stability under extreme conditions. Because now that scientists knew the positive charge was gathered into a tiny region, the next thing they had to face was almost embarrassingly direct. If that centre contains multiple positive charges pressed close together, then every one of them should repel the others. The closer they are, the stronger that repulsion becomes. Which means that in discovering the nucleus, physics had also stumbled into a new puzzle, one that would not politely go away. It had found a crowd of positive charges living far too close together for comfort, and somehow, against expectation, staying put. Once the atom had been stripped of its old simplicity and given a tiny central core, the next difficulty arrived almost immediately. In some ways, it was even more unsettling than the discovery of the core itself. A centre carrying positive charge was one thing. A centre carrying a great deal of positive charge, all crammed into an astonishingly small region, was another matter entirely. That was no longer just a structural detail, it was a problem with temperament. Positive charge does not behave kindly toward more positive charge. It does not welcome it, blend with it, or settle into harmony by default. It pushes away. It insists on distance. And yet here was the atom, apparently built around a central crowd of positive charges packed so tightly together that by all ordinary expectation they ought to have been desperate to part company. It is one of those moments in physics where a discovery immediately becomes an argument. The nucleus had been revealed because incoming particles sometimes met something hard and concentrated enough to send them sharply off course. That meant the atom contained a compact positive centre. But once you accepted that, you could not avoid the follow-up question. What exactly is crowded into that centre, and why does it remain there? You do not need advanced physics to feel the force of the puzzle. Even a child can understand the broad idea that some things repel. Like magnets with the wrong poles facing, they resist being pushed together. Electric charge behaves with a similar sort of stubbornness, though not in exactly the same way, and with much wider reach. Positive charge pushes positive charge away. It is not a rare or delicate effect. It is a basic rule of the electric world. So imagine gathering a handful of positively charged particles and pressing them into one confined space. Then imagine that space is not merely small, but unimaginably small, a region so tiny that the word cramped begins to feel wildly inadequate. The repulsion would not politely sit in the corner, it would dominate the conversation. Every positive particle would be pushing against every other positive particle. The more of them you added, the more complicated the situation would become. This is why the nucleus, once discovered, almost immediately stopped looking like a quiet centre and started looking like a packed argument held together by reasons not yet understood. In the early picture, before the neutron had entered the story clearly, the nucleus could easily be imagined as a cluster of positive charges, accounting for the central mass and the identity of the atom. That was not unreasonable as a first pass. The atom needed a positive centre. Different elements seemed to require different amounts of positive charge. There was a growing sense that this central count mattered deeply. But such a picture also created severe strain. If the nucleus was simply a collection of positive particles, then one had to explain how that collection survived its own internal hostility. It is rather like being told a group of people who all strongly dislike being near one another have agreed to spend eternity in a cupboard. At some point, even the calmest listener begins to ask practical questions. The practical question in this case was force. What could possibly be strong enough to keep those positive charges together? Electric repulsion is not a feeble thing. It reaches across distance. It does not switch itself off out of courtesy. Bring two positive charges close together and their mutual resistance becomes stronger, not weaker. Bring many together and the network of repulsions grows more tangled. Every proton, though that name would soon take on even greater importance, is not merely sitting in the nucleus minding its own business. It is being pushed on by all the other protons there. In a light nucleus, the problem is serious enough. In a heavy nucleus, it begins to look outrageous. It helps, perhaps, to linger with the ordinary intuition here, because the oddity of the nucleus can disappear too quickly once the terminology becomes familiar. We hear that a carbon nucleus has a modest number of protons, and that a lead or uranium nucleus has many more, and the statement slides by. But what it really means is that nature has found ways to maintain compact assemblies of mutually repelling positive charges in a space so tiny that no everyday analogy quite behaves. If you tried to reproduce the logic on a human scale, it would sound absurd. It would be like building a theatre out of people who all insist on standing as far from one another as possible, and then reporting that they remain happily compressed into the cloakroom. One would suspect either a very unusual agreement or an enforcer of legendary strength. At first, physicists did not yet know the full cast of characters inside the nucleus, but they could already see that positive charge was central to atomic identity. The number of those positive units in the nucleus determined what element the atom was. Change that number, and you did not merely alter the atom a little, you changed the atom into something else altogether. Hydrogen, helium, carbon, oxygen, iron, gold, uranium. These were not distinguished at the deepest level by their outer decoration, but by the positive charge concentrated in the nucleus. The centre was not just a heavy lump, it was an identity card. That made the crowd of positive charges even more consequential. It meant that the chemical richness of the world, the periodic table, the immense variety of substances and reactions, all rested on the existence of these charged central assemblies. Matter was not merely built from atoms. Atoms were classified by how many positive charges their nuclei managed to hold together. This is a remarkable thing when you pause over it. The periodic table is, in a very real sense, a list of successful nuclear arrangements, or at least arrangements that persist long enough to matter. Each element is a statement that nature found a way to keep a certain number of positive charges confined in a common core. Not all such statements are equally stable, of course, and that itself is a clue. Some nuclei are calm and durable, others are uneasy. Some endure for spans so vast that they might as well be permanent on human timescales. Others transform, emit particles or split. Even without knowing all the details yet, one can feel the pattern trying to emerge. If positive charge alone were the whole story, stable nuclei would be very hard to explain. The crowd would simply fly apart. Yet the world is full of nuclei that do not. Therefore, some additional ingredient or interaction must be present, something that binds more powerfully at very short range than electric repulsion can tear apart. But before that answer begins to sharpen, it is worth staying a little longer with the nature of the problem itself because it teaches a broader lesson about physics. Familiarity often hides difficulty. Once we learn the vocabulary of protons and nuclei, we may start speaking as if the existence of such objects were straightforward. In reality, they are extraordinary. A proton is not a little bead of positivity floating about in a harmless way. It carries a charge that contributes to a real and persistent force. A nucleus containing several protons is therefore not just heavier than a single proton, it is also internally contested. That internal contest is not an accident or a nuisance at the margins, it is part of what the nucleus is. The The difficulty becomes especially vivid when one considers heavier elements. A nucleus with one positive charge hardly has an internal crowd problem. There is no second proton to quarrel with. With two, the issue begins. With 6 or 8 or 20 or 50 or more, the cumulative repulsion is no longer a subtle background detail. Every proton is part of a densely packed parliament of mutual objection. If nothing stronger intervened, larger nuclei would be impossible. The periodic table would collapse almost as soon as it started. The world would be chemically poor, astronomically different, and very likely incapable of hosting the kind of long history that eventually led to you listening to this in whatever room now holds you. There is something pleasingly dramatic in that realization. The elements we take for granted exist because the nucleus is not merely a basket of positive charges. If it were, almost everything beyond the lightest atoms would be impossible. The richness of matter depends on a solution to a problem that at first glance looks nearly insoluble. That solution is hidden so deeply that for a long time scientists could only see its effects, not its mechanism. They knew something was preventing disaster. They did not yet fully know what. One useful way to think about the crowd of positive charges is to remember that the nucleus does not scale in comfort. As more protons are packed into the nucleus, the electrical repulsion among them becomes a greater burden. It is not simply that there are more particles. It is that there are more relationships of repulsion. Each added proton has its own push against all the others. This means the difficulty of keeping the nucleus together grows as nuclei become heavier. Stability becomes less automatic and more negotiated. Nature can manage it for many elements, but not without help, and not without limits. By the time one reaches the heaviest nuclei, the sense of strain is almost built into the object. Some of them seem less like eternal structures and more like tense agreements waiting for a reason to end. That, in fact, is part of the charm and terror of nuclear physics. It reveals that the quiet materials of the world are not always quiet in principle. A lump of uranium sitting unremarkably in rock is not a placid object because nothing interesting is going on. It is placid because the interesting thing happening inside it unfolds according to deep rules and very long odds. The internal challenge of positive charge has not vanished. It has been managed temporarily or conditionally by the arrangement nature has found. Sometimes that arrangement lasts, sometimes it slowly gives way. The nucleus is often stable, but it is never trivial. Earlier models of the atom had their own difficulties, but once the nucleus was in view, the challenge became much sharper. Positive charge was no longer spread out harmlessly through the atom. It was concentrated. That word matters. Concentrated means stronger local fields, stronger encounters, stronger reasons for repulsion to matter. A diffuse smear of charge can be conceptually tolerated in ways a compact charged core cannot. The nucleus forced physicists to take electrical repulsion seriously at a new scale of intensity. The problem could no longer be waved away with a gentle picture. It had become structural. This is also where the idea of atomic number began to take on its full significance. Different elements correspond to different numbers of positive charges in the nucleus. That is such a standard fact now that it almost sounds administrative, but it was a profound shift in understanding. The element was not defined by some vague overall character of the atom. It was defined by the count of positive charges at its centre. The nucleus, then, was not only the seat of mass, but the seat of identity. An identity itself depended on holding together a collection of mutually repelling charges. The universe, one begins to feel, has a taste for difficult arrangements. Naturally, scientists began probing that arrangement more carefully. Radioactivity had already revealed that atoms were not all eternally unchanged. Some nuclei transformed themselves, giving off particles or radiation. This was another sign that the nucleus was a dynamic and sometimes precarious place. A centre built from positive charges alone would seem especially vulnerable. If those charges repelled one another strongly, perhaps instability in radioactive nuclei was simply the truth of the matter beginning to show itself. But that could not be the whole story either. because many nuclei were perfectly stable, and even the unstable ones often survived for surprisingly long periods. The nucleus was neither a simple fortress nor an immediate catastrophe. It was something subtler and in a way more elegant. Because if the nucleus survives despite electric repulsion, then the force holding it together must have remarkable properties. It must be very strong at extremely short distances. It must be capable of binding the nuclear constituents closely enough to overcome the positive charges pushing outward. Yet it must also be limited in range, otherwise the structure of matter would look very different on larger scales. That is already a strange profile for a force. It is not the sort of thing we meet in everyday life. Gravity is weak but far-reaching. Electricity is strong and also far-reaching. The binding influence inside nuclei would have to be stronger still in its own little domain, while somehow remaining confined to that domain. A kind of ferocious local peacemaker. Before scientists fully understood that force, though, they still had another conceptual obstacle to clear. The mass of nuclei did not fit neatly with the idea that they were made only of positive charges. Something else seemed to be present. The counts did not line up comfortably if one tried to build every nucleus out of protons alone. This was not yet the full answer, but it was a growing discomfort, one of those small annoyances in science that often turn out to be doors. If the nucleus was not simply a cluster of positive charges, then perhaps part of the secret lay with a particle that added mass and binding possibilities without adding more electric repulsion. That possibility is one of the lovelier turns in the whole story, because it means the crowd of positive charges was never truly alone. The nucleus only looked like a pure parliament of positive objection from a partial vantage point. Once the full cast came into view, the problem did not disappear, but it became intelligible. There was another kind of resident in the nucleus, one that helped make larger assemblies possible, a neutral companion, silent electrically, but crucial structurally. The discovery of that fact would not only repair the bookkeeping of nuclear mass, it would transform the explanation of how nuclei exist at all. Still, before we meet that new arrival properly, there is value in keeping the raw puzzle alive a little longer, because the nucleus becomes much more interesting when you remember that its stability is not the obvious state of affairs. If you forget the problem of positive charge, the nucleus can start to sound like a simple central feature of atoms, a tiny ball of stuff that just happens to be there. But it is not just there. It is there against a clear and powerful tendency towards self-separation. Every stable nucleus is, in that sense, a small triumph of confinement. Every heavier element is a proof that nature found a way to keep a larger crowd together, without letting electric repulsion have the final word. And perhaps that is why this stage of the story feels so satisfying. The atom now has a centre. The centre contains positive charges. Those charges should repel each other strongly, yet nuclei exist. The contradiction is not a flaw in the story. It is the engine of the next discovery. Physics moves forward so often by this kind of pressure, where the facts line up just enough to make the missing piece impossible to ignore. The nucleus had been found. Its positivity had been recognised. Its internal difficulty had become obvious. Something essential was still absent from the picture. Some participant in the crowded centre that did not announce itself electrically but would prove indispensable once revealed. And as the evidence kept accumulating, that hidden companion began to step out of the dark. A crowd of positive charges is troublesome enough on its own, but the trouble grows even sharper once you try to count mass as well as charge. By the time physicists had accepted that the atom possessed a tiny central nucleus, they were no longer dealing with one mystery but several at once. The nucleus explained why some incoming particles in scattering experiments bounced away so dramatically. It explained why the atom had a concentrated centre. It offered a natural home for positive charge. But it also created a bookkeeping problem, and physics is rarely content to leave its bookkeeping untidy for long. The difficulty was this. If the nucleus contained the positive charge of the atom, then one might guess it was built entirely from positively charged particles. That sounds simple enough at first, almost temptingly simple. Count the positive charges, count the particles, and perhaps the nucleus is explained. But as measurements of atomic masses improved, that easy picture began to wobble. The mass of a nucleus was often much greater than the number of positive charges alone seemed able to account for. Something else had to be there. Something contributing weight without contributing extra positive charge. Something that would help explain how nuclei of the same element could differ in mass while remaining the same element. The nucleus was no longer just crowded, it was incomplete. This is where the story becomes especially satisfying, because it shows how science sometimes moves forward by discovering not what was flashy, but what was missing. The missing particle did not first announce itself with bright electrical behaviour. It did not glow, tug, or scatter in ways that made it instantly obvious. In a sense, it hid by being uncharged, and that made it difficult to catch. Charged particles are, from an experimental point of view, rather cooperative. They leave traces. They respond to electric and magnetic fields. They can be bent, steered, slowed, and detected more readily. A neutral particle is quieter. It does not advertise itself to the same instruments in the same cheerful way. If the nucleus contained a major neutral ingredient, then physicists were hunting something that did not volunteer its presence. There had already been hints that the simple proton-only picture could not be the whole story. Scientists had learned that atoms of the same element could come in versions with different masses. These were not different elements, because chemically they behaved as the same kind of atom. They occupied the same place in the periodic table. They had the same positive nuclear charge, and yet they were not identical in mass. Today we talk about isotopes with easy familiarity, but at the time this was an important clue. It said that atomic identity depended on one thing, while atomic mass could vary through another. The nucleus, then, could not be understood as a mere stack of positive charges and nothing more. Ernest Rutherford, who had already done so much to reveal the nuclear atom, suspected that a neutral nuclear constituent might exist. This was not a wild fantasy. It was a thoughtful response to a growing set of difficulties. If a neutral particle lived in the nucleus, then one could explain extra mass without extra charge. One could also begin to imagine a way to build nuclei that were not simply impossible crowds of mutually repelling positive particles. A neutral partner would not add to the electrical infighting. It might, in some deeper way, help stabilize the whole arrangement. But suspicion is not discovery, and physics always wants the harder thing. It wants evidence that will survive other people. The particle that changed the picture arrived properly in the early 1930s, and with it came one of those moments when an awkward collection of puzzles suddenly starts arranging itself into a coherent story. The key figure here was James Chadwick, a physicist working in a scientific world that had already become richly populated with clues, contradictions, and half-answers. Experiments had shown that certain nuclear reactions produced a strange penetrating radiation. At first, this radiation was interpreted as a very energetic form of gamma radiation, because it seemed to carry no charge and it could pass through matter rather effectively. But the more carefully physicists studied its effects, the less comfortable that explanation became. The setup involved bombarding light elements, especially beryllium, with particles emitted from radioactive sources. Something neutral seemed to come out. That neutral something then struck other materials and knocked protons out of them with surprising energy. If one insisted that the neutral radiation was simply an unusually fierce kind of gamma ray, the energy accounting became rather strained. The gamma rays would have needed to be implausibly energetic to explain what was observed. Chadwick looked at the evidence with a sharper eye, and saw that a different interpretation fit much better. The neutral radiation was not just radiation in the familiar wave sense. It was made of particles with substantial mass, roughly comparable to the proton, yet carrying no electric charge. That particle was the neutron. It is difficult to overstate how important that was. The neutron did not merely add one more item to the growing catalogue of subatomic entities, It repaired the atomic nucleus conceptually. Before the neutron, the nucleus was a charged puzzle with too much mass and too much internal repulsion. After the neutron, the nucleus became a mixed assembly of protons and neutrons, with atomic identity tied to the number of protons and mass shaped by the total number of both. The neutron gave the nucleus depth. It allowed physicists to stop pretending that positive charge alone could do all the work. There is also something wonderfully practical about the neutron as a solution. Because it carries no electric charge, it does not worsen the electrical repulsion inside the nucleus. That matters enormously. Add another proton and you add both mass and more positive push. Add a neutron and you add mass without adding that push. Suddenly the structure of heavier nuclei becomes more understandable, not yet fully explained, because the question of what actually binds protons and neutrons together still remains, but at least structurally intelligible. The nucleus is no longer a crowd of positive charges somehow enduring a permanent internal quarrel. It is a crowd of positive charges supported by neutral companions that change the balance. This also cleared up the mystery of isotopes in a particularly elegant way. Atoms of the same element share the same number of protons and therefore the same core identity, but they can differ in how many neutrons accompany those protons. That means they can have different masses without ceasing to be the same element. Carbon remains carbon, whether its nucleus contains one neutron count or another, because its proton count remains fixed. Hydrogen, too, can come in forms with differing neutron content. The periodic table became sharper because the neutron allowed scientists to separate two ideas that had previously been entangled. Identity comes from protons. Nuclear variety within an element comes from neutrons. There is a pleasing economy in that. The proton tells you what the atom is. The neutron helps tell you which version of that atom you're dealing with, and often whether its nucleus is likely to be stable or restless. The proton is the badge. The neutron is part of the support staff, though that perhaps undersells it badly. In truth, the neutron is less like staff, and more like the quiet engineer without whom the entire building would be uninhabitable. And the building, let us be honest, still looked precarious. Because discovering the neutron solved one class of problems immediately, but it also sharpened the next question. If the nucleus is made of protons and neutrons, what keeps them all together? The proton problem had not vanished. Protons still repel one another electrically. That remains true no matter how many neutrons are present. The neutron helps because it adds nuclear substance without adding electrical strain. But that alone does not explain why protons and neutrons stay bound in such a tiny volume. The neutron changed the cast of characters. It did not yet reveal the full script. Still, the improvement was immense. Before the neutron, physicists had sometimes entertained rather convoluted pictures of nuclear structure, in which electrons might somehow live inside the nucleus in order to help balance things conceptually. Those pictures were increasingly awkward. The neutron removed the need for many of those strained arrangements. Nuclear composition became cleaner. A nucleus was built from protons and neutrons, together known as nucleons. That language itself reflected a conceptual settling. The nucleus was no longer an improvised storage box of unexplained ingredients. It was a specific kind of system with specific constituents. From that point onward, the shape of nuclear physics changed noticeably. Researchers could begin classifying nuclei in a more orderly way. They could ask not just how many positive charges were present, but how many neutrons accompanied them. They could track which combinations produced stable nuclei and which led to decay. They could examine why some nuclei were unusually tightly bound, while others were prone to transformation. The neutron did not answer every question, but it turned a foggy puzzle into a map with the roads. There is another reason the neutron was such a profound discovery, and it has to do with access. Because neutrons carry no electric charge, they do not face the same electrical barrier when approaching nuclei that charged particles do. A positively charged particle heading toward a positively charged nucleus meets repulsion immediately. It must push uphill, so to speak, against that electric resistance. A neutron does not have that problem. It can enter the nuclear neighbourhood without announcing itself electrically. This made neutrons extraordinarily useful as probes and triggers of nuclear reactions. In time, that quiet neutrality would become one of the most consequential facts in modern history, because it would help make controlled and uncontrolled chain reactions possible. The uncharged particle did not just explain nuclei, it opened doors into them, but we need not rush to the later consequences yet. It is enough for now to appreciate how thoroughly the neutron rearranged the mental picture. The atom now had a nucleus composed of two kinds of particles, one positively charged, one neutral. The electrons lived outside that nucleus, shaping chemistry and the atom's external behaviour. The nucleus itself carried most of the mass. Different elements differed by proton number. Different isotopes differed by neutron number. The central object of matter, once imagined as a featureless final grain, had become a compact many-body system with a real internal census. And perhaps what is loveliest about the neutron is how much it demonstrates the value of not forcing nature into tidy expectations too early. If physicists had insisted too rigidly that everything important in atomic structure must be charged and easy to track, they might have delayed the truth much longer. The neutron required patience with indirect evidence. It required taking seriously the idea that the nucleus might contain something almost invisible to the common methods of detection. Science often rewards that sort of patience. The world is under no obligation to arrange itself according to the easiest laboratory habits. James Chadwick's work was therefore not just a discovery of a particle, it was an act of intellectual house-cleaning on a grand scale. It swept away a clutter of increasingly awkward assumptions and replaced them with a simpler, more robust account of nuclear structure. There is a special pleasure in that kind of progress. Sometimes science advances by becoming more complicated. Sometimes it advances by finding the missing piece that makes everything else less absurd. The neutron was very much that piece. It also changed the emotional tone of the nucleus. Before, the nucleus could seem like an almost impossible collection of positive charges, a kind of microscopic act of defiance against electricity. After the neutron, the picture became more nuanced. The nucleus was still tense. The protons still repelled one another, but now there were neutral partners in the mix helping make compact nuclear assemblies possible. The nucleus began to look less like an impossible crowd and more like a carefully balanced coalition. Not peaceful, perhaps, but workable. Workable, however, is not the same as fully understood. Once the neutron was on the stage, one deeper mystery stood out more clearly than ever. Protons and neutrons must be held together by some force powerful enough to overcome electrical repulsion at very short distances. This force had to act strongly inside the nucleus, and yet not dominate ordinary life on visible scales. You do not feel nuclear binding in your fingertips when lifting a spoon. Chairs do not cling to walls because of it. The force clearly operated in a tiny realm, and with astonishing intensity there. That is a very particular demand to place on nature. It means the nucleus is governed by an interaction unlike the familiar ones of daily experience. The discovery of the neutron also helps scientists understand why nuclei do not all behave the same way. Some nuclei have the right balance of protons and neutrons to remain stable for immense durations. Others are off balance and tend to transform. In lighter nuclei, roughly equal numbers of protons and neutrons often work well. In heavier nuclei, more neutrons are usually needed to offset the increasing electrical repulsion among the larger number of protons. This does not mean neutrons are little passive cushions stuffed in between the protons. Though that cartoon has its charm, it means that the deeper binding interaction cares about both protons and neutrons, and the right proportion matters. Nuclear stability turns out to be less like stacking blocks, and more like tuning an instrument. A little too much one way or the other, and the note begins to wobble. That realization would eventually lead to rich ideas about nuclear structure, shells, binding energies, and patterns of decay. But even here, at this stage, the basic picture is already vastly improved. The nucleus is not only the tiny centre of the atom, it is a system made of protons and neutrons, with identity fixed by the number of protons and stability deeply influenced by how many neutrons are present. That is a huge step away from the earlier years when the atom was still imagined as a sort of homogeneous lump with electrons embedded in it like fruit in cake. One can also see why the neutron felt to many physicists like a discovery that made the invisible world more believable. Strange as the nucleus still was, it became less arbitrary. Before, there had been too many loose ends. Why was the mass so large? Why did isotopes exist? How could nuclei be built sensibly? After the neutron, the atomic story acquired a better grammar. Things fitted. The hidden centre of matter stopped behaving like an untidy miracle and began behaving like a difficult but lawful system. And yet the lawful part only deepened the next challenge. Because if neutrons and protons inhabit the nucleus together, something must bind them both. Not just proton to neutron, but proton to proton and neutron to neutron in the nuclear sense. The force responsible cannot simply be electricity, because electricity would only worsen the proton crowding and would ignore the neutral neutron in the wrong way. Nor can it be gravity, which is far too weak at these scales to manage such intimate and energetic confinement. The answer has to be another kind of interaction altogether, one whose grip is fierce enough to hold the nucleus together, where every ordinary intuition expects separation. So the neutron changed the picture in exactly the way the best discoveries do. It did not close the subject down. It made the subject clearer and more demanding at once. It solved the mass puzzle. It explained isotopes. It gave the nucleus the right population. It made sense of atomic identity without forcing impossible arrangements. But by doing all that, it also illuminated the real engine room of the problem. The nucleus was now understood well enough that its central miracle could no longer be ignored. Protons and neutrons were there together in a tiny space, and something extraordinarily strong had to be keeping them that way. The atom had found its missing particle. The next step was to understand the force that made that mixed little crowd hold fast instead of coming undone. Once the neutron had taken its place in the story, the nucleus stopped looking like an impossible ball of pure positive charge and started looking like a more balanced, if still deeply tense, little assembly. That was real progress, but it did not let anyone relax for very long. In some ways, it made the central mystery harder to ignore. A nucleus was now understood as a compact collection of protons and neutrons. The protons carried positive electric charge. The neutrons did not. The protons still repelled one another. The neutrons helped with mass and stability, but they were not magical peacemakers by mere presence alone. So the question sharpened. What actually holds the nucleus together? Electricity could not be the answer. That much was now obvious. Electric attraction can hold electrons near a positive nucleus in the atom as a whole, but inside the nucleus itself, the key electrical relationship among protons is repulsion, not attraction. Gravity could not be the answer either. Gravity does pull matter together, and it is the great architect of stars, planets, galaxies, and the large-scale structure of the universe. But at the scale of the nucleus, gravity is absurdly weak. It is so weak there that it barely deserves a chair in the room. If you tried to explain nuclear stability by gravity, it would be like trying to hold a castle wall in place with a polite breeze. The numbers simply do not work out. Something else had to be present. Something powerful enough to overwhelm the electrical push of the protons at very short distances. This is where nuclear physics becomes wonderfully serious. Because the force required is not just stronger than the electricity in some vague or occasional way. It has to be strong enough, under exactly the right conditions, to keep nucleons packed into an incredibly small region, despite all the pressure toward separation. That means the force has to be fierce. Not merely noticeable, not merely helpful, fierce. It must grab hold at close range with a grip that outmuscles the electric repulsion, trying to prise the nucleus apart. The name we give this grip is the strong nuclear force. though even that phrase needs a bit of care, because there are two related ideas that often get blended together. One is the deeper fundamental strong interaction that binds quarks inside protons and neutrons. The other is the effective force between protons and neutrons inside the nucleus, often called the residual strong force. For the purposes of understanding the nucleus as a compact assembly, it is this residual force that matters most directly. It is, in a sense, the leftover power of the deeper strong interaction, leaking out from within the nucleons and creating an attraction between them when they are very close together. That phrase, leftover power, may sound suspiciously casual for something so important, but it captures an essential truth. Protons and neutrons are not elementary particles in the way electrons are treated in simple atomic theory. They are built from quarks, and those quarks are bound by gluons through the deeper, strong interaction. Inside each proton and neutron, that binding is immense. The residual force between nucleons is not the whole original force in its rawest form, but a kind of spillover effect from that internal binding structure. If that sounds a little like saying the nucleus is held together by the aftertaste of an even more fundamental violence, that is not entirely unfair. What matters for the nucleus is that when protons and neutrons come very near one another, this residual attraction becomes strong enough to dominate the situation. At those tiny separations, it can beat electric repulsion. That is the crucial point. The protons do indeed push one another apart electrically, but when a proton and neutron, or two protons or two neutrons are close enough, the strong nuclear attraction can seize control of the local argument. It can hold them together. Notice, though, that the phrase close enough is doing a great deal of work. This is not a long-range force like gravity or electricity. It does not stretch out across the atom in any meaningful way. It is intensely short-ranged. That is one of the reasons it remained hidden for so long in everyday experience. You do not notice the strong nuclear force between yourself and a chair across the room, because it does not reach across rooms. You do not notice it between two atoms sitting comfortably apart in a molecule, because it is not meant for that scale. It is a force of near contact, almost of intimacy. It comes into play only when nucleons are packed into extremely close quarters. That short-range character is essential. In fact, it is what makes the force so perfect for the job and so peculiar at the same time. If it were weak and long-ranged, it would fail to stabilize nuclei. If it were strong and long-ranged, matter would behave in wildly unfamiliar ways on larger scales. Every lump of stuff might cling to every other lump of stuff with ridiculous enthusiasm. The world would become sticky in a manner that no one would enjoy. Instead, the force is powerful, but local. It governs the nucleus without taking over the visible universe. It is as if nature hired an exceptionally muscular security guard and then told him he was only allowed to work in one very small room. That room, of course, is crowded. And the crowding matters because the strong nuclear force is not simply a universal invitation for nucleons to fall into one another without limit. If that were all it did, nuclei would collapse into an even denser mess than they already are. In reality, the strong interaction between nucleons has a more nuanced behaviour. At the very closest distances, it becomes effectively repulsive. That detail is easy to overlook, but it is crucial. The force does not just pull nucleons together, it also prevents them from occupying the same place in some naive classical sense. There is an equilibrium of sorts, a preferred closeness. Too far apart and the attraction fades. Too close and a hard-core repulsion appears. The nucleus is not a random pile. It is a tightly packed system arranged within these rules. This is one of the reasons nuclear matter is so strange. The nucleons are bound strongly but not glued into a featureless blob. They move, jostle, occupy quantum states, and experience a force that attracts at one range and resists at another. The nucleus is therefore not well pictured as marbles fixed in permanent contact. It is better thought of as a compact quantum, many-body system where the constituents are confined, correlated, and held by a short-range interaction far more powerful than anything ordinary intuition prepares us for. That sounds grand. but what it means in plain terms is that the nucleus is not static furniture. It is more like a tense little community whose members can never leave the building but still have complicated internal relations. You can begin to see why electricity alone would never tell the story. Electricity would simply say that the protons are pushing outward all the time, and the more protons you add, the more severe that outward pressure becomes. The strong nuclear force replies that nearby nucleons attract one another powerfully enough to stay bound. The competition between these two tendencies is the basic drama of the nucleus. Electric repulsion pushes the protons apart. Strong nuclear attraction binds nucleons together at close range. Stability emerges where the balance works. Instability appears where it does not. This balance also explains why neutrons matter so much. A neutron does not add electric repulsion because it carries no charge, but it does participate in the strong nuclear interaction. In effect, it contributes binding without adding to the electrical quarrel among protons. That makes it invaluable, especially in heavier nuclei. As the number of protons rises, the total electrical repulsion inside the nucleus rises as well. More neutrons are then needed to help provide enough additional strong binding to keep the whole assembly together. This is why heavier stable nuclei tend to contain more neutrons than protons. Nature needs extra neutral help as the positive crowd grows harder to manage. There is something very elegant in that arrangement. The neutron is not a passive filler. It is an active participant in the force network that gives the nucleus its cohesion. Without neutrons, the strong attraction among the protons themselves would not be enough to build large stable nuclei. The periodic table would be much shorter and much duller. The richness of matter depends on the fact that the strong force binds neutrons and protons together in a way that lets nuclei grow beyond the lightest elements. When you hold a piece of iron or calcium or copper, you are holding the outcome of that delicate triumph. Delicate, however, does not mean weak. This is the part of the story where words can be misleading. We often use delicate to mean fragile in the everyday sense, like a teacup or a social situation involving relatives and politics. Nuclear delicacy is different. It means the structure depends on a precise competition among very powerful effects. A nucleus is not held together by something faint. It is held together by one of the most intense interactions in nature, operating at a scale so small that its ferocity is hidden from ordinary view. The nucleus is calm from the outside because the violence of the inner balance is perfectly contained. And this explains something that often surprises people when they first think about nuclear energy. How can such tiny objects be associated with such enormous releases of energy? The answer is that the forces involved in binding nucleons are immense. Rearranging a nucleus is not like nudging furniture around a room. It is more like altering the terms of a compact agreement enforced by a terrifyingly strong local authority. When a nucleus changes configuration, splits, fuses, or decays in certain ways, the energy differences involved can be very large. That is not because nuclei are enormous. It is because the forces that organize them are. The short-range nature of the strong force also helps explain why the electrical problem gets worse in heavier nuclei. Each nucleon feels strong attraction, mainly from its nearest neighbors. The strong nuclear force does not efficiently reach across the entire nucleus in the way electric repulsion does. Electric repulsion among protons, by contrast, accumulates across the whole collection. Every proton repels every other proton, so as nuclei get larger, the strong force does not simply scale up its binding effect without limit. It saturates in an important sense. A nucleon mainly binds to nearby companions. The electrical repulsion, however, keeps adding up over many proton pairs. This means that larger nuclei become harder to stabilize. The strong force is mighty, but it is local. Electricity is weaker in the immediate close-range contest, but it is more persistent across the entire proton crowd. That single fact explains a surprising amount of nuclear behavior. It helps explain why there is no stable nucleus of unlimited size. It helps explain why heavy nuclei need a surplus of neutrons. It helps explain why the heaviest nuclei are often unstable and prone to radioactive decay. They are not badly made. They are simply trying to hold together under conditions where the local binding strength of the strong force is increasingly burdened by the long reach of proton repulsion. It is rather like trying to run a large organization where every person has a direct complaint against every other person, while the management team can only speak effectively to those standing nearby. At some point, the paperwork becomes impossible. Even so, it is astonishing how much the strong nuclear force can accomplish. It permits nuclei with dozens of protons to exist. It allows stars to build heavier elements. It gives the universe a chemistry rich enough for rocks, oceans, atmospheres, metals, and living bodies. Without it, matter would be confined largely to the simplest nuclei. Hydrogen would dominate in an even more overwhelming way than it already does. The higher elements that make planets and organisms possible would struggle to form or persist. The world around you would lose much of its substance and variety. It is not too dramatic to say that the strong force is one of the quiet reasons there is a world worth describing. There is another layer to all this, and it is one of the most beautiful. The strong nuclear force does not just solve the problem of repulsion, it creates structure. Because nucleons are quantum objects, they do not merely clump in arbitrary ways. They occupy states, form patterns, and produce especially stable arrangements under certain conditions. This is where later ideas about shell structure and magic numbers will come in, though we need not rush there yet. The main point for now is that once the strong force is in the story, the nucleus becomes not just possible but richly organized. Stability is not random, it has patterns. Some nuclear arrangements are especially favored, others are strained. The force that outmuscles electricity does not merely prevent disaster, it creates architecture. Still, it is worth keeping our feet on the ground and not letting the word strong become too abstract. Strong compared with what? Strong enough to do what? The cleanest answer is this. It is strong enough, at nuclear distances, to bind nucleons together despite the electrical repulsion among protons. That is why nuclei exist. It is also strong enough that changing nuclear arrangements can involve very large amounts of energy. But it is not strong in a vague cinematic sense. It has limits. It acts only over very short distances. It does not rescue every imaginable nucleus. It does not prevent all forms of decay. It is not a magical universal glue. It is a very specific interaction with a very specific range, and nuclear stability is what happens when that interaction wins the local contest well enough. The phrase wins the local contest is worth hanging on to, because it reminds us that the nucleus is always a negotiated object. The strong force is winning, yes, but electricity is still in the room. The protons are still pushing outward. In a stable nucleus, they are not content. They are contained. That difference matters. The nucleus is not stable because repulsion has been turned off. It is stable because repulsion has been outmatched under the right conditions. This gives the nucleus its permanent air of controlled tension. It is one of nature's best examples of order produced not by the absence of conflict, but by the dominance of one rule set over another in a very confined arena. This also means that when the balance is shifted, interesting things happen. If a nucleus becomes too heavy, or if its neutron-to-proton ratio drifts too far from what works best, the strong force may no longer be able to guarantee long-term stability. Then radioactive decay appears, or in some cases fission becomes possible. The nucleus begins to seek a more favourable arrangement. It may emit a particle, transform one nucleon into another, or split into smaller nuclei altogether. All of these processes are expressions of the same deeper fact. The strong force is powerful but not infinitely permissive. There are boundaries to what can be held together. In a strange way, that makes the force more impressive, not less. A force that held absolutely everything together without discrimination would not create the rich landscape of nuclear behaviour we actually see. The beauty of the strong interaction at the nuclear level is that it creates both stability and variety. It allows many nuclei to exist, but not all. It favours some arrangements strongly. tolerates others temporarily, and rejects the most imbalanced over time. The result is a periodic table with a history, radioactive chains, stellar element formation, and a nuclear world that feels less like a static inventory, and more like an ecosystem of possible structures. And perhaps this is the right place to notice how much our original question has evolved. At first, we asked what a nucleus really is, and why it should fly apart. We then found the nucleus as a tiny central core, discovered that it contains a crowd of positive charges, and saw how the neutron transformed the picture. Now we can say something more satisfying. A nucleus is a compact system of protons and neutrons bound by a short-range interaction, strong enough to overpower electric repulsion at close distances. That is not the whole truth, but it is already far richer than the old image of a little central bead. Yet one final piece of unease remains, and it is an important one. Even after you know that a force stronger than if electricity is at work, you're still left with a natural question. If nuclei are held together by such enormous binding power, what does that actually mean in terms of mass, energy, and stability? Why does holding something together make the whole system lighter than the sum of its parts? Why can breaking or reshaping a nucleus release such tremendous energy? In other words, once the force is in place, the next thing we have to understand is the cost and consequence of binding itself. Because the nucleus is not just a crowd held in check. It is a crowd whose very togetherness changes the accounting of matter and energy in a way that still catches people off guard the first time they see it clearly. And this is where the nucleus becomes especially interesting, because once you know that a powerful binding force exists, it is very tempting to think the problem has been settled. Protons and neutrons are held together by the strong nuclear force, so that is that. The nucleus stays intact, the atom keeps its centre, and the rest is just detail. But that would be a little too comfortable, and the nucleus is never quite that polite. Even after we understand that something strong is doing the holding, the unsettling truth remains that the nucleus still has very good reasons to come apart. In fact, if you look at the situation honestly, flying apart is in some sense the thing it ought to want to do. That sounds dramatic, but it is really just a matter of following the conditions carefully. Inside the nucleus, protons are packed extremely close together. Every proton carries positive electric charge. Every proton therefore repels every other proton. This is not a small background effect. It is not some minor inconvenience that can be ignored, while the real physics gets on with more important business. It is one of the central facts of nuclear life. The nucleus is not merely a place where binding happens. It is a place where binding must constantly overcome a very real push toward separation. One reason this can be easy to underestimate is that the word nucleus sounds compact and settled. It gives the impression of something dense and self-assured, perhaps even inevitable. But if you mentally strip away the strong binding force for a moment, what remains is not a calm little sphere. What remains is a tight cluster of positive charges, all pressing against one another at extremely short distances. That cluster would not sit there patiently. It would burst outward. The repulsion would win at once. There would be no heavy elements, no broad periodic table, no quietly durable matter on the scales we know. The nucleus survives only because another interaction intervenes at close range with extraordinary strength. The pressure toward breakup never disappears. It is merely outmatched. This matters because it changes how we think about stability. We often speak of a stable nucleus as though it were simply content, as though nature had found a comfortable resting place and put its feet up. But nuclear stability is not comfort in that sense. It is not the absence of internal pressure. It is a balance in which one very strong influence manages to outweigh another very strong influence under very specific conditions. The nucleus should fly apart in the sense that electric repulsion is always there, always pushing outward, always making larger charged assemblies harder to hold together. When a nucleus remains intact, it does so under tension. A good way to feel that tension is to remember how electric forces behave. Electricity is not a short-range whisper. It reaches. Every proton in the nucleus repels every other proton, not just the nearest ones, not just a favoured few, but all of them. That means the burden of repulsion grows as the nucleus gets larger. Add one more proton to a nucleus, and you do not merely add one more particle. You add a new source of repulsion acting against all the other protons already present. This is why the difficulty of nuclear stability rises so sharply in heavier elements. The strong nuclear force binds mostly among close neighbours, but electric repulsion keeps adding itself across the whole group. That difference in range is one of the deepest reasons the nucleus should fly apart. The strong force is very powerful, yes, but it is local. It does its best work only when nucleons are extremely close. The electrical repulsion among protons, by contrast, does not care nearly so much about being confined to nearest neighbours. It accumulates through the whole proton population, so as nuclei grow larger, the strong force does not simply gain unlimited control. It cannot effortlessly bind every proton to every other proton across the entire nucleus in some grand universal embrace. Its reach is too short for that. Meanwhile, the electrical quarrel keeps spreading through the whole crowd. That is why very large nuclei are such difficult objects. They are not merely bigger versions of small nuclei. They are more strained versions. You can think of it like this. Imagine a room full of people where each person strongly dislikes being close to every other person. Now imagine that the only thing holding the group together is a set of intense but very local friendships. Each person is deeply attached to a few immediate neighbours, but remains in active disagreement with many others across the room. In a small gathering, that may be manageable. In a large gathering, the total atmosphere becomes much harder to control. The local friendships do real work, but the broader field of mutual irritation keeps growing. That is not a perfect analogy, because nuclei obey quantum rules rather than social ones, but it captures the basic imbalance. Short-range binding does not automatically cancel long-range repulsion. This is why heavy nuclei always have something faintly precarious about them, even when they are long-lived on human timescales. They are examples of nature doing difficult bookkeeping. The strong force binds nearby nucleons together strongly enough to create a coherent object, but the electric repulsion among the many protons is always trying to swell the nucleus outward or make it seek a less stressful arrangement. In lighter nuclei, the problem is manageable. In heavier nuclei, the strain becomes much more pronounced. By the time you reach the largest naturally occurring nuclei, the question is no longer why instability sometimes appears. The question is how stability lasted at all. The role of neutrons becomes even clearer when viewed from this angle. Neutrons contribute to nuclear binding through the strong interaction, but they do not add electric repulsion. That is extremely useful. It means a nucleus can increase its strong binding support without worsening the positive charge problem. In light nuclei, roughly balanced numbers of protons and neutrons are often sufficient. In heavier nuclei, extra neutrons become necessary because the growing proton repulsion needs additional neutral support. A heavy nucleus with too few neutrons is in a dangerous position. It has too much internal electrical pressure relative to the binding help available. Such a nucleus is more likely to transform or decay. But neutrons do not solve everything. They help the nucleus resist breakup, but they do not turn the positive charges into polite housemates. They do not erase the long-range repulsion, and they cannot make arbitrarily large nuclei stable forever. There comes a point where adding more protons creates too much electrical difficulty for the available strong binding to handle gracefully. This is why the heaviest nuclei tend to be unstable. Even with generous neutron support, the internal push towards separation becomes too hard to suppress indefinitely. The nucleus begins to look less like a settled home and more like a structure under continual mechanical stress. One of the reasons this subject matters so much is that it helps explain why radioactive decay is not some bizarre exception to an otherwise calm atomic universe. Radioactive decay is in many cases the nucleus revealing its strain. A nucleus that cannot quite maintain the best balance of forces may change itself into a more favourable arrangement. It may emit a particle, it may convert one kind of nucleon into another. In especially large nuclei, it may split into smaller pieces. These are not random acts of microscopic drama. They are ways in which a nucleus responds to the fact that flying apart, or at least rearranging toward less internal tension, is often energetically tempting. That phrase, energetically tempting, points towards something important. When we say the nucleus should fly apart, we do not necessarily mean that every nucleus is on the verge of exploding in the ordinary sense. We mean that the internal competition of forces creates a genuine pressure toward separation, and the nucleus survives only when its particular arrangement is bound tightly enough to resist that pressure. If a different arrangement offers lower overall energy, the nucleus may eventually find a path toward it. Sometimes that path is easy, and the nucleus changes quickly. Sometimes it is difficult, and the nucleus endures for immense stretches of time before changing. But the fact that such changes exist at all is a reminder that the nucleus is never just sitting there for no reason. It is an arrangement earned against competing possibilities. This is especially vivid in the largest nuclei. The heavier the nucleus, the more the electric repulsion among protons adds up, and the more the object resembles something trying to maintain its shape under pressure from within. There are nuclei so large that one can almost picture them as droplets under stress, pulled together by one set of influences and pushed outward by another. This is not merely a visual metaphor. Some models of nuclear behaviour really do borrow ideas from liquid drops, because there is a useful resemblance in how cohesion and surface effects compete with internal pressure. In such a picture, the nucleus is never far from the question of division. If the internal repulsion becomes too strong, splitting into smaller nuclei can become favourable, because the smaller pieces may manage their charge more comfortably than the larger original object. This, of course, is one of the roots of nuclear fission. A very heavy nucleus may be only conditionally stable. Disturb it in the right way, and it may deform, stretch, and divide into two smaller nuclei plus additional particles. The reason this can release so much energy is tied directly to the internal stress we have been talking about. The large nucleus contains a difficult concentration of positive charge. Breaking it into smaller charged assemblies can reduce that difficulty overall. The nucleus, in effect, moves from one tense arrangement to arrangements that make better use of the available binding. Again, we are drifting toward the topic of binding energy, which deserves its own careful treatment. But even without the full accounting, you can already see the principle. Large nuclei do not merely sit on a shelf of existence. They sit under rules that make alternative arrangements matter. Another important reason the nucleus should fly apart is that the strong force itself is not a simple universal glue. It does not increase without limit as you add more and more nucleons. A given nucleon interacts strongly only with nearby partners. This means that the binding benefit of adding additional nucleons does not scale in the same runaway way as the electrical repulsion among protons. In a very rough sense, each nucleon can only enjoy the company of a limited number of neighbours strongly enough to gain much extra binding from them. But each proton contributes its repulsion to many others across the nucleus. This asymmetry creates a built-in ceiling on how easy large nuclei can be to stabilise. So the nucleus should fly apart not because nature forgot to design it properly, but because the rules themselves create a permanent competition. The strong force wins locally. Electricity keeps objecting globally. Neutrons help. Quantum structure helps. Certain arrangements are especially favourable. But the outward push never disappears. The larger the proton count, the more severe that push becomes. Stability is real, but it is conditional. If you ever want to appreciate how remarkable an ordinary piece of matter really is, it helps to remember that each of its nuclei is a successful answer to a problem that easily could have gone the other way. There is also the matter of shape. We often imagine nuclei as neat little spheres because spheres are tidy, and textbook artists deserve an occasional rest. But nuclei are not always perfectly spherical, especially as they become larger. They can be slightly stretched or otherwise deformed. Once shape enters the story, the pressure toward breakup can become even more interesting. A distorted nucleus may allow repulsive effects to express themselves more strongly in certain directions, and if the binding cannot comfortably restore the shape, the object may be more vulnerable to change. In very heavy nuclei, one is not dealing with a rigid ball, but with a quantum system whose internal structure and collective motion can matter greatly for whether it remains intact. Then there is tunneling, one of those quantum ideas that feels almost deliberately designed to annoy classical common sense. Even if a nucleus is protected by a barrier that seems to prevent immediate breakup, quantum mechanics allows small but real probabilities for particles or clusters to escape through that barrier without needing to go over it in the classical sense. This is part of what underlies certain kinds of radioactive decay. A nucleus may be held together well enough that breakup is not immediate, yet still have a finite probability of losing part of itself over time. So even a nucleus that looks classically secure may possess a quiet route toward change. The message remains the same. Holding together is not automatic, it is statistical, conditional, and sometimes temporary. What makes all of this so rich is that stable nuclei are not accidents either. It would be wrong to say that because the nucleus should fly apart, stability is somehow mysterious in a hopeless way. Stability can be understood. It arises from the strong interaction, from the right mix of protons and neutrons, from quantum structure, and from the existence of arrangements that are energetically favourable enough to persist. But those arrangements are impressive precisely because there are so many good reasons for them not to work. The nucleus is not a simple box of particles. It is a pact agreement among repulsion, attraction, range, balance, and quantum rules. That agreement is easier to maintain in some cases than others, and that is why the phrase "should fly apart" is so useful. It forces us to look past the calm surface of matter and see the real terms of the problem. If all you knew about the nucleus was that it contains several positive charges in a tiny volume, then breakup would seem inevitable. The fact that this does not happen for many nuclei means something significant must be lowering the overall cost of staying together. The nucleus is not refusing logic. It is obeying a deeper logic than first impressions reveal. This deeper logic also explains why the line between stable and unstable nuclei is not arbitrary. It is patterned. There are combinations of protons and neutrons that work especially well. Others are merely workable for a while. Others fail almost immediately. The whole nuclear landscape is shaped by the competition between binding and breakup. Nature is not drawing random lots. It is exploring which compact charge systems can actually survive under the rules available. That is why the chart of known nuclei has such structure. It is a map of what can be held together, and for how long before the tendency toward flying apart finds a route to express itself. At this point, one begins to see why nuclear physicists care so much about energy bookkeeping. It is not enough to know that one force beats another in some loose wrestling match. We need to know how much energy is tied up in a given arrangement, how much is required to pull it apart, and why a bound nucleus can weigh less than the separate ingredients from which it is made. That last point often surprises people the first time they meet it properly. A bound nucleus is not just a pile of protons and neutrons sitting close together. Its very togetherness changes the accounting. Some of the mass of the separated ingredients effectively shows up as binding energy when the nucleus forms. That means the nucleus is lighter than the sum of its free parts, and it is exactly this difference that tells us how much work would be needed to pull it fully apart. So when we say the nucleus should fly apart, we are really standing on the edge of the next and perhaps most important idea. The nucleus contains strong reasons to separate, especially because of proton repulsion. Yet if it is bound, pulling it apart requires energy. That sounds almost backwards until you realize what binding really means. The intact nucleus sits in a lower energy state than the separated particles. Its mass reflects that. To break it, you must pay the difference. And once you begin to see the nucleus in that light, not merely as a crowded little object, but as a system whose stability is written into the balance between mass and energy, the whole subject becomes sharper because the next step is to understand how binding itself leaves a measurable mark on what the nucleus weighs and what it can give back. Now we arrive at one of the strangest turns in the whole subject, because the nucleus does not just stay together through force alone, it also changes the bookkeeping of matter itself. This is the point where many people first feel that nuclear physics has stopped being merely small and difficult and has started behaving almost unfairly. A nucleus is made from protons and neutrons. Those are real particles with real masses. So the obvious expectation is that if you take a certain number of protons and neutrons, add their masses together, and then compare that total with the mass of the nucleus they form, the answer should be the same. After all, why should putting things together make any of the mass go missing? And yet that is exactly what happens. A bound nucleus weighs less than the separate protons and neutrons that went into it. Not by accident, not because the measurements are sloppy, and not because nature is trying to be cute. It weighs less because when those particles become bound together, some of the mass that the separate ingredients possessed is no longer sitting there as mass in the same way. It has been converted into binding energy. The nucleus is, in a very literal sense, cheaper than its ingredients. That difference between what the separate nucleons would weigh on their own and what the finished nucleus actually weighs is one of the clearest signs that binding has taken place. This is the strange logic of binding energy. To make a nucleus, energy must be released. Because energy and mass are deeply equivalent, releasing energy means the final bound system has less mass than the unbound pieces. If you then want to pull the nucleus apart again, you must put that energy back in. The missing mass was never really lost in the everyday sense. It was transformed into the energy released when the nucleus formed, and the energy you would have to repay if you wish to undo that binding completely. The first time people hear this, it can sound like a trick of language. It is not. It is one of the most concrete and measurable ideas in modern physics. The nucleus does not just contain particles. It contains a history of what it cost, or rather what it paid out to become a bound system. Its mass records that history. A stable nucleus sits at a lower energy than the same protons and neutrons wandering free. That lower energy state corresponds to a lower total mass. This is why the nucleus can resist flying apart, not because there is no pressure toward breakup, but because the bound arrangement is energetically favourable enough that separating everything fully would require work. That phrase, energetically favourable, is worth slowing down for because it is the heart of the matter. In physics, systems often prefer lower energy arrangements. A ball rolls downhill rather than uphill. A hot object cools if it can. A stretched spring relaxes when released. The nucleus is more subtle than those examples, but the principle is related. When protons and neutrons bind into a nucleus, the resulting system can sit at lower energy than the same particles in isolation. The difference is not invisible bookkeeping done by theorists in a back office. It is physically real. It shows up in measurements. It shows up in nuclear reactions. It shows up in the enormous energies that can be released when nuclei are rearranged into more tightly bound forms. This is where the strong nuclear force and the repulsion among protons come together in a more mature way. Earlier, it was enough to say that the strong force outmuscles electricity at very short range, allowing nuclei to exist. But that only describes the contest in terms of forces. Binding energy describes the result in terms of what kind of state the nucleus has become. A nucleus is not simply a crowd held in place against its will. It is a bound state whose total energy is lower than that of the fully separated particles. That lower energy is the reason it does not immediately come apart. To separate it, you must climb back up. Another way to say it is that a stable nucleus sits in a kind of valley. The free protons and neutrons are at a higher level. When they come together and bind, they move downward energetically, and the difference must go somewhere. It can emerge as radiation, as motion of other particles, or as other forms of released energy depending on the process. Once that energy has left, the nucleus is settled in a lower state. If you later wish to recover the original unbound particles, you must provide at least that much energy from outside. You have to pay the full price of breaking every nuclear bond that matters in the arrangement. This is why the phrase binding energy is so useful. It means the amount of energy required to disassemble the nucleus completely into its separate protons and neutrons. It is also the amount of energy that would be released if those separate nucleons came together from rest and formed the nucleus in the first place. The two views are the same story told in opposite directions. One is construction, the other is demolition. The number is the same because nature keeps a strict account even when the logic feels strange. There is something especially satisfying about this because it turns the earlier question on its head. We asked why the nucleus should fly apart. Binding energy answers by saying that for a stable nucleus, complete separation is not the preferred energetic arrangement. Yes, the protons repel one another. Yes, the nucleus contains internal tension. But the combined effect of the strong interaction and the quantum structure of the nucleus is such that the whole bound object sits lower in energy than the separated ingredients. Flying apart would require an energy investment, so the nucleus does not remain intact because the repulsion is fictional. It remains intact because the bound state wins the overall accounting. Still, the accounting is not the same for all nuclei. This is where the subject becomes even richer, because the amount of binding per nucleon varies from one nucleus to another. Some nuclei are only weakly bound compared with others. Some are especially tightly bound. That variation is the hidden key to understanding why both fusion and fission can release energy, even though at first glance they seem like opposite processes. Light nuclei can release energy by joining together. Very heavy nuclei can release energy by splitting apart. This sounds contradictory until you realize that what matters is not whether nuclei are becoming larger or smaller, but whether the final arrangement is more tightly bound than the initial one. If the products of a nuclear reaction are more tightly bound overall, the excess energy can be released. If they are less tightly bound, energy must be supplied. Binding energy is therefore not just a detail about what holds a nucleus together. It is the master logic behind nuclear power in stars, nuclear reactors on Earth, and much of the large-scale history of the elements. A useful example lies with the lightest nuclei. Very small nuclei are not, in general, the most tightly bound per nucleon. If two light nuclei combine into a somewhat heavier one that is more tightly bound, the new nucleus has a lower total energy relative to its ingredients, and energy is released. This is the basic reason fusion can power stars. In the core of the Sun, hydrogen nuclei ultimately end up contributing to the formation of helium through a chain of processes. The final helium nucleus is more tightly bound than the original collection of hydrogen nuclei and associated particles. The difference appears as released energy, which is why the Sun shines instead of merely looking busy. At the other end of the scale, very heavy nuclei are also not the champions of binding efficiency. They are burdened by the growing electric repulsion among their many protons. If such a nucleus splits into two medium-sized nuclei that are each more tightly bound per nucleon, then again energy is released. This is the basis of nuclear fission. A very heavy nucleus such as uranium is not at the absolute bottom of the energetic valley. It is a large, stressed arrangement that can reduce its overall energy by dividing into more favourable pieces. When it does, the difference appears as released energy. The astonishing part is that both of these possibilities follow from the same overall curve of nuclear binding. Light nuclei can go downhill by joining. Heavy nuclei can go downhill by splitting. Somewhere in the middle lies a region of especially tightly bound nuclei, where the binding per nucleon is near its maximum. Iron is often mentioned here because nuclei around that region are among the most tightly bound. They are, in a sense, hard to improve upon energetically through either fusion or fission. That fact has enormous consequences in astrophysics. It helps explain why ordinary stellar fusion does not go on forever, making ever heavier elements while continuing to release energy in the same easy way. Once you get near the most tightly bound region, the simple downhill road runs out. But before we wander too far into stars, it is worth returning to the core idea in a more personal and concrete way. Imagine you had a group of separate protons and neutrons far apart from one another. Each of those particles contributes its own mass. Now imagine bringing them together under the right conditions so that they form a stable nucleus. As the bound state forms, energy is released. Because energy and mass are equivalent, the final nucleus has less mass than the sum you started with. If you place that final nucleus on a fantastically precise scale and compare it with the separate particles on equally fantastical scales, the difference is there. Small in ordinary units, perhaps, but profound in meaning. The scale is not merely weighing matter, it is reading the memory of binding. That phrase, memory of binding, is not standard textbook language, but it is a useful intuition. The mass of the nucleus tells you that something happened when the nucleons came together. They did not merely pile up like stones, they settled into a bound state and paid out energy to do so. The reduced mass is a permanent record of that payout. This is why nuclear mass tables are so valuable to physicists. By comparing masses carefully, one can infer binding energies, decay possibilities, reaction outcomes, and the relative stability of different nuclei. The masses are not passive labels, they're compressed stories. This also helps explain why nuclear reactions can be so much more energetic than chemical reactions. In chemistry, the important energy changes come from rearranging electrons in atoms and molecules. Those energy scales matter greatly for life, technology, fire, metabolism, and all the familiar business of ordinary matter. But the electrons live far from the nucleus compared with the scale of nuclear binding. Chemical reactions are about outer structures. Nuclear reactions are about the compact core where the strongest local interactions in ordinary matter reside. Rearranging nuclei therefore taps into a much deeper layer of energy accounting. That is why a tiny amount of nuclear fuel can release so much energy, compared with a far larger amount of chemical fuel. The difference is not that chemistry is trivial, it is that the nucleus plays for much higher stakes. Binding energy also explains why some nuclei are stable and others are not in a more precise way. A nucleus may be bound overall, meaning it would take energy to tear it completely into separate protons and neutrons, and yet still be unstable against some particular decay mode if there exists a path to a lower energy arrangement. This is an important subtlety. Stability is not all or nothing in the simplest sense. A nucleus can be held together enough not to disintegrate instantly, while still being able to lower its energy by changing into another nucleus, perhaps by emitting a particle, or through a transformation involving one nucleon becoming another type. The nuclear world is full of these layered possibilities. This is why radioactive decay can coexist with the idea of binding. A radioactive nucleus is not necessarily unbound in the crude sense of barely hanging together like a badly packed suitcase. It may still be a genuine bound system. But there may be another arrangement available that is even more favourable energetically, and quantum mechanics may allow a route toward it. Over time, the nucleus takes that route. So the strange logic of binding energy does not divide nuclei into simply bound and unbound. It creates a landscape of more or less favourable states, with different pathways between them and different barriers that may slow or hasten change. One of the most instructive examples is alpha decay in heavy nuclei. Certain heavy nuclei can lower their energy by emitting a compact cluster made of 2 protons and 2 neutrons. That cluster is itself a tightly bound little nucleus. The parent nucleus does not explode wholesale. Instead, it finds a more favourable arrangement by shedding a particularly stable package. The fact that this happens at all reflects the binding logic on both sides. The emitted cluster is tightly bound, and the daughter nucleus plus the emitted cluster together can sit at lower total energy than the original parent alone. Again, the nucleus is always negotiating its internal bookkeeping. The same logic runs through beta decay, though in a different way. A nucleus with an unfavourable balance of protons and neutrons may lower its energy by converting one type of nucleon into the other through the weak interaction. The total arrangement becomes more favourable, and energy is released in the process. Here too, binding energy is part of the deeper story. The nucleus is not changing out of boredom. It is moving toward a more favourable state under the rules available to it. What makes binding energy so powerful as an idea is that it unifies so many apparently different phenomena. It explains why nuclei can exist at all, despite internal repulsion. It explains why mass is missing from bound systems. It explains why stars can shine by fusion and why heavy nuclei can split. It explains the broad pattern of nuclear stability. It explains why some isotopes persist and others transform. It even explains why the nucleus, though tiny, commands such disproportionate importance in the history of the universe. Once you understand binding energy, the nucleus stops being just a cramped little bundle of particles and becomes a system whose mass, stability, and possible transformations are all tied together by one very strict and very strange logic. There is also a deeper philosophical satisfaction in it, if that does not sound too grand for a late evening discussion of subatomic bookkeeping. Binding energy teaches that the whole is not always just the sum of the parts. In daily life, that phrase gets used rather carelessly, usually by people trying to make a committee meeting sound inspiring. In nuclear physics, it is literally true in a measurable way. The whole nucleus is less massive than the sum of its isolated pieces, because the act of binding changes the total energy of the system. The parts in company are not equivalent to the parts in isolation. Their relationships matter. Their configuration matters. The energy of being together matters. This is a lesson that repeats all through physics. Systems acquire properties through interaction, not merely through inventory. A molecule is not just a list of atoms. A crystal is not just a pile of ions. A nucleus is not just a basket of nucleons. Structure changes the bookkeeping. Arrangement changes what the system is capable of. And in the nucleus, this truth is concentrated into one of the clearest and most dramatic forms nature offers. So when we speak of binding energy, we are really speaking of the price of separation and the reward of formation. We are speaking of why the nucleus can resist the urge to fly apart, and why certain nuclear changes can unleash energies that dwarf chemistry. We are speaking of the fact that a stable nucleus lives lower than its isolated ingredients, and that its mass carries the evidence. Once you see that clearly, the nucleus feels less like a paradox and more like a carefully balanced account written in the language of mass and energy. The next step, though, is to look more closely at how nuclei organize themselves internally, because binding energy tells us that some arrangements are favored more than others, but it does not yet tell us why certain specific numbers of protons or neutrons produce especially stable nuclei, or why some nuclei behave almost like droplets, while others reveal shell-like structure more reminiscent of electrons in atoms. The nucleus is not only bound, it is patterned, and the deeper we look, the more it becomes clear that even in this tiny crowded core, nature has more than one way of organizing order. Up to this point, the nucleus has already done enough to earn a bad reputation for being difficult. It is tiny, crowded, full of protons that repel one another, dependent on a short-range force of enormous strength, and governed by binding energy rules that sound almost designed to irritate common sense. But there is another surprise waiting once you look more carefully. The nucleus is not just held together, it is organized. Not always in the same way, not always in a way that fits one simple picture, but organized nonetheless. And that means that if we want to understand what a nucleus really is, we cannot stop at the fact that it is bound. We have to ask how that binding arranges itself. This is where nuclear physics becomes especially satisfying, because the answer is not a single tidy model that works for every purpose. Instead, physicists found that nuclei reveal different aspects of themselves depending on what question you ask. Sometimes a nucleus behaves in ways that make it look almost like a droplet of nuclear matter, with something like surface tension and a tendency toward deformation and splitting. At other times, it behaves as though its protons and neutrons occupy shell-like patterns, a bit like electrons in atoms, with especially stable configurations appearing at certain favoured numbers. Both pictures are useful. Neither one tells the whole story alone. The nucleus, being itself, refuses to be captured by a single simple image, when two overlapping ones will make the matter much richer and slightly more inconvenient. Let us start with the shell picture, because it is one of the clearest signs that the nucleus is not just a random heap of protons and neutrons pressed together by force. If that were all it were, then nuclear stability would vary in a rather featureless way. One might expect gradual trends, perhaps, but not sharp patterns. Yet experiments showed that some nuclei are noticeably more stable than their neighbours, in ways too regular to ignore. Certain numbers of protons or neutrons appeared especially favourable. Nuclei with those counts often had greater stability, distinctive binding behaviour, and reduced eagerness to be distorted. These favoured counts became known as magic numbers, which is one of those scientific terms that sounds almost playful until you realise it points to a deep structural fact. The key magic numbers are 2, 8, 20, 28, 50, 82, and 126. When a nucleus has one of these numbers of protons or one of these numbers of neutrons, it often enjoys extra stability. When both proton number and neutron number are magic, the nucleus can be especially robust. This was not something one would naturally guess from a simple liquid-like picture, or from the idea of the nucleus as merely a crowd of particles all jostling in the same general volume. It suggested that protons and neutrons were arranging themselves in discrete quantum states within the nucleus, filling those states in an orderly way. Once a shell was filled, the system gained a kind of structural satisfaction. Adding another nucleon then meant starting a new shell, which changes the behaviour quite noticeably. There is an obvious comparison here with electrons in atoms. Electrons occupy shells around the nucleus, and filled shells give rise to the familiar structure of the periodic table and the special stability of noble gases. Nuclear shells are not the same thing. They occur inside the nucleus itself, not around it, and they involve protons and neutrons in their own separate sets of states. Still, the analogy is close enough to be extremely helpful. Just as filled electron shells create certain patterns in chemistry, filled nuclear shells create patterns in nuclear stability. The nucleus, then, is not merely held together by brute force. It has an internal architecture shaped by quantum rules. This architecture was not obvious at first. In fact, one of the reasons the nuclear shell model was such an achievement is that the nucleus looks, on the surface, much less like a neat layered system than the atom does. Electrons live in a broad cloud around a compact centre. That naturally invites images of levels and shells. The nucleus, by contrast, is so small and dense that it is easy to imagine all the nucleons simply muddled together, yet the evidence kept pointing to something more ordered. Certain nuclei were unusually stable. Certain reaction patterns made more sense if nucleons occupied specific states. The shell idea gradually became unavoidable. One of the crucial insights that made the shell model work properly involved something called spin-orbit coupling, though I will keep the language gentle here. The basic point is that the motion of a nucleon inside the nucleus and the intrinsic angular character it carries interact in a way that reshapes the energy ordering of the available states. Without this effect, the shell structure would not produce the observed magic numbers correctly. With it, the pattern falls into place far more successfully. This was one of those moments in physics where a model goes from promising to persuasive, because a missing detail suddenly makes the whole arrangement line up with reality. So what does the shell picture tell us in ordinary terms? It tells us that protons and neutrons inside the nucleus are not all equivalent in how they are arranged. They fill available states, and some complete configurations are especially favourable. A nucleus with filled shells can be more tightly organised and less easily disturbed. It may be more spherical, less ready to deform, and often more stable against certain kinds of decay or excitation. This is why nuclei such as helium-4, oxygen-16, calcium-40, lead-208, and a few others have a particularly notable place in nuclear structure. Their proton and neutron counts line up with shell closures in ways that make them unusually well behaved by nuclear standards, which is saying rather a lot. But if the shell model were the whole story, nuclear behaviour would be too rigid and too tidy compared with what is actually observed. Many nuclei, especially those away from closed shells, behave collectively rather than just as individual nucleons occupying separate states. They can deform, they can vibrate, they can rotate. Their properties often resemble those of a little drop of nuclear fluid more than those of a set of neatly independent particles filling levels one by one. This is where the liquid drop picture enters, and it earns its place not as a rival to the shell model, but as a complement to it. The liquid drop model treats the nucleus somewhat like a tiny drop of incompressible fluid. That comparison is not perfect, of course, because a nucleus is a quantum many-body system, not a literal droplet you could pour, spill, or regret dropping on the carpet. Still, the analogy captures several important features. Nucleons bind mainly to nearby neighbours, rather like molecules in a drop of liquid. There is something like a bulk contribution to the binding, since nucleons in the interior enjoy many close neighbours. There is also something like a surface effect, because nucleons near the outer edge have fewer neighbours and therefore contribute differently to the overall binding. On top of that comes the electric repulsion among protons, which tends to push the nucleus apart and becomes increasingly important as proton number rises. This droplet-style picture turns out to be extraordinarily useful for understanding broad trends in nuclear masses and stability. It helps explain why binding energy per nucleon changes the way it does across the chart of nuclei. It helps explain why very heavy nuclei become less stable as electrical repulsion accumulates. It helps explain why fission becomes possible, because a large charged droplet can lower its energy by deforming and splitting into smaller droplets under the right conditions. If you want to understand the overall balance of nuclear cohesion and proton repulsion on a large scale, the liquid drop model gives a beautifully intuitive account. There is something especially elegant about the way the droplet picture handles the shape of the nucleus. A spherical shape is often favoured because it minimises surface area for a given volume, much as it does for ordinary liquid droplets. That helps with cohesion, but in very heavy nuclei, the growing electric repulsion can make deformation more attractive. The nucleus may stretch a little, becoming more elongated. If the balance tips far enough, the shape can move towards scission, the point at which one nucleus becomes two. This is not just a vague artistic image. It captures something real about how nuclei can collectively change form. A nucleus is not always a hard little ball. It can have shape, and shape can matter a great deal. That fact alone is worth pausing over. We often meet the nucleus first as a dot in a diagram, perfectly round and perfectly simple, like a sensible logo someone designed during a lunch break. But real nuclei can be spherical, slightly squashed, stretched, or capable of shifting between different shapes. Some even show what is called shape coexistence, where different structural arrangements lie unusually close in energy, and the nucleus can effectively display more than one character depending on how it is examined. One moment it seems almost spherical, another more deformed. The nucleus once again refuses to be just one thing. What makes this especially interesting is that the shell and droplet pictures often tug in different directions, and the actual behaviour of a nucleus reflects the competition between them. Near magic numbers, shell effects are strong. They tend to favour more rigid and often more spherical nuclei. Away from closed shells, collective effects can grow more important. The nucleus may then behave more like a deformable drop, with many nucleons participating in coordinated motion rather than merely sitting in individually filled states. In other words, some nuclei are more shell-dominated while others are more collective. Most of the nuclear world lies somewhere in the negotiation between these two tendencies. This is why nuclear structure can feel so alive once you get past the first intimidating layer. The nucleus is not built on a single mechanical principle repeated endlessly. It has regions of behaviour. Some nuclei are almost textbook examples of shell closure and extra stability. Others are soft and easy to deform. Some rotate like little quantum tops when excited. Others vibrate more like breathing drops. Some have patterns that make sense only when one remembers the separate shell structures of protons and neutrons. Others are best understood through bulk properties and collective motion. The nucleus is a tiny system, but it supports a remarkable range of internal organisation. A particularly nice example of shell behaviour is the existence of doubly magic nuclei, where both proton number and neutron number are magic. These nuclei often stand out as especially stable and tightly structured. Helium-4 is a familiar light example. Lead-208 is a famous heavy one. Such nuclei tend to resist deformation more strongly than their neighbours, and can act almost like structural anchors in the landscape of nuclear physics. They remind us that the nucleus is not just a bag of particles held by average forces. Certain exact arrangements matter. Meanwhile, the liquid drop picture helps us understand something equally important but more global. It explains why there are general trends in nuclear binding that do not depend on the fine details of shells alone. It explains why larger nuclei often need more neutrons for stability. It explains why the heaviest nuclei live under increasing stress from proton repulsion. It explains why splitting a very heavy nucleus can be favourable. In that sense, the drop model gives us the large-scale map, while the shell model gives us the local street names. You need both if you want to navigate honestly. There is a deeper lesson here too. In many parts of physics, systems can display both single particle behaviour and collective behaviour depending on the scale or question. Solids can be described in terms of individual electrons and also in terms of waves moving through the whole crystal. Fluids can be understood molecularly and also through bulk properties like pressure and flow. The nucleus belongs to that same broad family of objects that are most revealing when viewed from more than one angle. If you insist on only one language, you lose something essential. The shell model captures quantized structure. The liquid drop model captures collective cohesion and deformation. The actual nucleus uses both. This becomes especially vivid when we think about excited nuclei. A nucleus is not always in its lowest energy state. It can absorb energy in a reaction and move into an excited state. What happens then depends strongly on its structure. A shell-dominated nucleus may show excitations that look like promoting individual nucleons into higher states. A more collective nucleus may show vibrations of shape or rotational motion of a deformed whole. These are not mere metaphors. They are measurable patterns, with characteristic sequences of excited levels and transitions that reveal the internal character of the nucleus. In other words, by studying how a nucleus responds when nudged, physicists can tell whether it is behaving more like an orderly shell system or more like a soft collective drop. Rotation is one of the loveliest examples. A perfectly spherical nucleus does not lend itself easily to ordinary rotational patterns in the same way a deformed nucleus does. But a nucleus that is stretched or squashed can rotate, and the energy levels associated with that rotation form recognizable sequences. Observing such sequences is strong evidence that the nucleus has an intrinsic shape, rather than being simply a featureless sphere. So when nuclear physicists talk about deformed nuclei rotating, they are not indulging in picturesque speculation. They are reading a structural fact from the spectrum. Vibration offers another clue. Some nuclei can oscillate around an average shape, becoming slightly more or less elongated, or shifting in other collective ways. Again, this resembles the behaviour of a droplet more than the behaviour of independent particles. The nucleus, then, is not frozen. It can tremble as a whole. That fact will matter even more once we start talking about decay and fission, because some of the same collective motions that make a nucleus soft or excitable can also prepare the way for larger structural changes. There is also the question of why shell effects weaken or strengthen in different regions. The answer lies partly in how full the available proton and neutron states are, and partly in how collective behaviour emerges when there are enough nucleons outside closed shells to interact in coordinated ways. A nucleus with just a few nucleons beyond a shell closure may still carry a strong memory of the closed shell core. A nucleus with many active nucleons outside such closures may become much more collective. It begins to act less like a tidy shell arrangement, with a few add-ons, and more like a deformable whole. This is one reason the nuclear chart is so rich. Moving from one isotope to the next can shift the balance gradually or, in some regions, rather suddenly. All of this helps answer a question that often lurks in the background. What is a nucleus really? Is it a little ball of nuclear fluid? Is it a quantized arrangement of particles in shells? Is it a deformed object with shape and rotation? The only honest answer is yes, depending on what aspect you're asking about. That is not an evasion. It is the reality of a complex quantum system. The nucleus is not obliged to fit one school diagram. It has both microscopic and collective structure. The best descriptions are the ones that know when each language is doing useful work. It also means that the word core in ordinary speech is more revealing than it first appears. We often use core to mean the central essence of something. In the atom, the nucleus truly is that. But it is not a plain centre. It is layered behaviour. It can be more rigid or more soft, more shell-like or more droplet-like, more spherical or more deformed, more stable or more eager to rearrange. The shape of the core is not an idle detail. It affects how the nucleus reacts, what energies it prefers, what decays are possible, and whether it can be pushed towards splitting. This is especially important in the heaviest nuclei. There, shell effects can provide pockets of extra stability against the enormous electrical repulsion that would otherwise make such nuclei even more short-lived than they are. In other words, shells do not just matter for light and medium nuclei. They also matter in the far heavy region, where they can help prop up nuclei that the liquid drop picture alone might consider especially vulnerable. This interplay is part of the reason physicists have long been interested in the possibility of an island of relative stability among very heavy nuclei. The broad droplet tendency pushes toward instability, but shell structure may grant local support in certain places. The nucleus keeps finding ways to turn one simple question into several more specialized ones. If there is a common thread through all this, it is that nuclear order is never one-dimensional. Binding alone does not explain everything. Proton repulsion alone does not explain everything. Shell filling alone does not explain everything, nor does the droplet picture. The nucleus is a place where short-range force, long-range repulsion, quantum states, collective motion, and shape all meet in a confined volume. That is why it can be so hard to summarize honestly and so rewarding once the pieces start to connect. By now, the atomic nucleus looks much less like a static pellet, and much more like a compact structured system with preferred arrangements, favoured counts, and a capacity for collective behaviour. Some nuclei are stiff and self-contained, others are soft and ready to move, some are protected by filled shells, others behave like charged droplets under stress, some hold their shape almost stubbornly, others can vibrate, rotate, or edge toward deformation in ways that hint at future change. And once you begin to see the nucleus in those terms, the next part of the story becomes hard to resist, because a structured object like this does not simply sit forever. It can tremble, it can split, it can decay. Under the right conditions, the patterns inside the core begin to express themselves not just as shape and stability, but as motion and transformation. If the nucleus were nothing more than a rigid little lump, then the story would be much easier to tell. We could say that protons and neutrons gather in the centre of the atom. The strong force holds them together, electric repulsion tries to pull the protons apart, and stability is the result when the balance works. That would not be wrong exactly, but it would leave out one of the most important truths about nuclear life, which is that nuclei are not still in the deep sense. Even when they are bound, even when they're stable for vast stretches of time, they are not frozen objects like tiny lead marbles sealed in glass. They can be excited, they can shift shape, they can vibrate, rotate, rearrange themselves, and in some cases break apart or transform into something else altogether. The nucleus is not just a centre, it is a centre with moods, if one allows a very careful use of the word. This matters because once you understand that the nucleus has structure, shape, and binding energy, the next natural question is what happens when that structure is disturbed, or when its arrangement is not the most favourable one available. The answer is that nuclei can tremble, split, or decay, and each of those possibilities reveals something about the tensions hidden inside matter. A nucleus may sit quietly for ages, or it may change in the blink of an eye. It may release a little energy, or an astonishing amount. It may emit a single particle, or divide into two substantial fragments. What looks like one tiny object from afar turns out to be a whole landscape of possible behaviours. A good place to begin is with the idea of an excited nucleus. Just as electrons in atoms can occupy higher energy states and later drop down, emitting radiation, nuclei too can be excited above their lowest energy arrangement. This can happen in collisions, in radioactive processes, or in reactions where one nucleus absorbs a particle or a bit of energy from its surroundings. Once excited, the nucleus is not usually eager to stay that way. It tends to seek a lower energy state if one is available. And since it is a quantum system, those lower states are not continuous in just any old way. They come in allowed arrangements, so an excited nucleus often sheds its excess energy by emitting a very energetic packet of electromagnetic radiation known as a gamma ray. Gamma emission is in some ways the gentlest kind of nuclear change, because the identity of the nucleus need not change at all. The number of protons remains the same. The number of neutrons remains the same. The nucleus simply moves from a higher energy state to a lower one, rather like a tense person finally sitting down after insisting for too long that they were perfectly comfortable standing. But even this gentlest nuclear process reminds us that the nucleus is not static. It has internal arrangements. It has excited states. It can carry excess energy and then let it go. Sometimes the story is not so mild. Some nuclei are not merely excited. They are unstable in a more fundamental way. Their proton to neutron balance may be unfavourable. Their total size may create too much internal electrical strain. Their structure may permit a route to a lower energy arrangement through the emission of a particle, or through a transformation of one nucleon into another. When that happens, we call the process radioactive decay. The word radioactive can feel charged with modern anxieties, and for understandable historical reasons, but in its basic scientific sense, it simply means that a nucleus changes spontaneously because a more favourable state is available, and the rules allow a path toward it. There are several main ways this can happen, and each one teaches a different lesson about the nucleus. One of the oldest and most intuitively graspable is alpha decay. In alpha decay, a heavy nucleus emits a compact cluster made of 2 protons and 2 neutrons. This cluster is itself a tightly bound little nucleus, the nucleus of helium. The parent nucleus loses that package and becomes a different nucleus with fewer protons and fewer neutrons. This is a remarkable thing when you slow down and look at it honestly. The nucleus does not disintegrate into random scraps. It spits out a very specific little bundle, one that happens to be especially stable in its own right. That is already a clue that nuclear structure matters. The alpha particle is not a casual fragment. It is a favoured configuration. In certain heavy nuclei, shedding such a cluster lowers the total energy and produces a more stable daughter nucleus. But the most elegant part of alpha decay is the way it happens at all. Classically, one might think the alpha particle is trapped inside the nuclear potential and should not be able to escape unless it has enough energy to climb over the barrier created largely by electric repulsion outside the short-range binding region. Yet quantum mechanics allows a different route. The alpha particle has a finite probability of tunnelling through the barrier and escaping, even when it would not have enough energy to do so in an ordinary classical picture. This idea of tunnelling is one of the quiet marvels of the microscopic world. It means that a nucleus can be secure enough to remain intact most of the time, while still allowing rare escapes that add up over long periods. The difference between one radioactive lifetime and another can come down to very small differences in energy and barrier shape, which affect the tunnelling probability enormously. That is why some alpha-emitting nuclei decay quickly, while others take far longer. The nucleus is not choosing a moment. It is living under probabilities. Over time, the probabilities do their patient work. beta decay tells a different sort of story. Here the nucleus changes not by ejecting a tightly bound cluster, but by altering the identity of one of its nucleons. A neutron can change into a proton, or a proton into a neutron depending on which direction leads to a more favourable balance. These processes involve the weak interaction rather than the strong force or electromagnetism, and they are accompanied by the emission of lighter particles. The end result is that the nucleus moves toward a more stable proton to neutron ratio. This is why beta decay is so important for nuclei that have too many neutrons, or too many protons relative to what works best. There is something especially revealing about beta decay because it shows that nuclear stability is not just about how tightly everything is bound in a crude sense. It is also about composition. A nucleus may be well enough held together not to fly apart immediately, and yet still be unstable, because a different internal balance of protons and neutrons would be more favourable. In such a case, the nucleus can change one nucleon into the other type and move downhill energetically. It is not abandoning the whole nuclear structure. It is adjusting the membership list. That adjustment can have major consequences, because changing one proton into a neutron, or vice versa, changes which element the nucleus belongs to. So beta decay is not just a small internal correction, it is transmutation. One element becomes another, quietly, lawfully, and without asking chemistry for permission. This was one of the great shocks of early radioactivity studies. Matter, once imagined as made of fixed and eternal atomic kinds, turned out to contain nuclei that could transform themselves. Not all at once, not in arbitrary ways, but according to specific rules. The old dream of permanent indivisible identity began to unravel. The nucleus introduced history into matter. A given atom might not simply be what it is forever. Its nucleus might be a stage in a sequence, a moment in a decay chain that leads through other nuclei over time until a more stable endpoint is reached. Those decay chains are another reminder that nuclear life is often a journey rather than a single event. A very heavy unstable nucleus may undergo alpha decay, producing a daughter nucleus that is itself unstable and then decays again, perhaps by beta decay, perhaps by another alpha emission, perhaps by several steps in succession. Over time, the whole chain walks down the landscape of possible nuclei toward a stable region. The process can involve many transformations, each one lawful, each one guided by the availability of lower energy arrangements and by the interactions that permit the necessary change. There is also spontaneous fission, which is in some ways the most dramatic expression of a nucleus giving up on being one piece. In spontaneous fission, a very heavy nucleus splits into two substantial fragments, usually with a few neutrons thrown out as well. This is not the same as alpha decay, where a small, stable cluster peels off from a much larger parent. Fission is a far more radical reorganization. The nucleus deforms, stretches, and ultimately divides. The reason this can happen goes back to the competition we have been following all along. Heavy nuclei contain many protons, and the electrical repulsion among them imposes serious internal stress. The strong force binds the nucleus locally, but it cannot erase the growing burden of long-range proton repulsion. In the heaviest nuclei, the balance becomes delicate enough that splitting into two smaller nuclei can lower the total energy. One can picture the process cautiously as a charged drop that begins to elongate. At first, the strong nuclear cohesion and surface-like effects resist the distortion. But if the nucleus enters the right state, or if quantum tunneling takes it through the barrier that separates one shape from another, the deformation can grow until the waist narrows and the nucleus divides. The resulting fragments are themselves nuclei, usually more stable or at least more favourable than the original giant parent in energetic terms. The released energy can be immense, and the extra neutrons that emerge can matter enormously for what happens next. Those emitted neutrons are the quiet hinge on which much of 20th century history turned. Because neutrons carry no electric charge, they can approach other nuclei without having to fight the same electrical barrier that protons do. In certain heavy nuclei, absorbing an extra neutron can push the nucleus into a more unstable state, and trigger fission. If one fission event releases more neutrons, and those neutrons in turn trigger more fissions, a chain reaction becomes possible. If controlled, this can produce energy steadily in a reactor. If uncontrolled and fast enough, it can produce the explosive release that gave the modern world one of its darkest and most consequential technologies. But even apart from those historical consequences, neutron-induced fission is scientifically beautiful because it shows how delicately the nucleus balances on the edge between one shape and another. A single extra neutron can be enough to tip the accounting. The heavy nucleus, already under internal tension from its many protons, finds itself in a state where the path to splitting becomes more accessible. The chain reaction then becomes a kind of collective conversation among nuclei, each fission event throwing out neutrons that go on to ask the same difficult question of others. Will you stay one object, or would you energetically rather be two? Not all nuclei that can fission will do so easily. The precise likelihood depends on nuclear structure, barrier shapes, neutron energies, and other details. This is part of what makes nuclear engineering and nuclear astrophysics such demanding fields. One cannot simply say that heavy nuclei split and leave it there. Some are more likely to do so, some need encouragement, some are poor candidates for sustaining a chain reaction. The nucleus, as ever, insists on specifics. Half-life enters the story here as one of the most useful and most misunderstood concepts in radioactivity. When we say a radioactive nucleus has a certain half-life, we do not mean that each individual nucleus contains a little internal clock that goes off at a scheduled moment. We mean that for a large population of identical nuclei, there is a characteristic timescale over which about half of them will have decayed. Each individual decay remains probabilistic. Any given nucleus may decay early, late, or not within the interval at all. The law lives in the statistics. This is another point where everyday intuition can struggle a little. We are used to causes that operate at specific moments. Nuclear decay is lawful without being scheduled in that way. The probability is stable even though the individual event is not predictable in advance. There is something strangely calming in that, once one gets over the initial irritation. The nucleus is not behaving capriciously, it is behaving quantum mechanically. Large numbers reveal precise regularity. Small numbers reveal irreducible uncertainty. Both are true at once. That is why radioactive dating works so well for old materials. The half-lives are dependable on the statistical level, even though the fate of any particular nucleus is not. It is also worth remembering that decay is not always a sign of a nucleus barely hanging together in a crude mechanical sense. A nucleus can be quite well bound overall and still radioactive if there exists a lower energy path accessible through one of the permitted processes. This is why radioactive nuclei can sometimes survive for very long periods. They are not unbound chaos. They are structured systems with limited but real roads toward more favourable arrangements. The pace of travel along those roads depends on barriers, probabilities, and the interaction involved. Alpha decay may be slowed by tunnelling difficulty. Beta decay may depend on the weak interaction and on the exact energy balance available. Spontaneous fission may be suppressed by a substantial deformation barrier. The nucleus is not simply choosing between staying and exploding. It is exploring a very specific menu of possibilities. Excited nuclei can also produce delayed behaviour. In some cases, a nucleus formed in a reaction or decay does not immediately settle all the way to its ground state. It may become trapped in a long-lived excited condition called a metastable state. Such a nucleus is still the same isotope in terms of proton and neutron count, but its internal energy arrangement is elevated and can persist for an unexpectedly long time before releasing gamma radiation. This is another reminder that the nucleus is structured enough to support not just one identity, but distinct internal configurations with different lifetimes. Even its excited life can have layers. Then there are collective tremors. A nucleus need not decay to show that it is dynamic. It can vibrate around an average shape. It can rotate if deformed. It can absorb energy in one encounter and release it in another. These motions are not decorative flourishes. They are evidence that the nucleus is a responsive many-body system. A vibrating nucleus is not coming apart, but it is revealing that the protons and neutrons inside it can move in coordinated ways. The whole core can breathe, stretch, or wobble. For a system that textbook diagrams often reduce to a coloured dot, that is a rather impressive amount of internal personality. These collective motions also influence how nuclei react. A soft nucleus that deforms easily may be more susceptible to certain kinds of excitation or fission. A rigid nucleus near a shell closure may resist deformation more strongly. In this way, the structure we discussed earlier and the transformations we're discussing now are part of one continuous story. Shape affects stability. Shell effects affect decay probabilities. Collective behavior affects reaction pathways. The nucleus does not keep its architecture separate from its future. The two are intimately linked. All of this has a large cosmic role as well. Many of the elements in the universe are created or modified through chains of nuclear reactions and decays in stars or stellar explosions. Nuclei capture particles, become excited, better decay toward stability, sometimes split, sometimes survive. The chart of nuclei is not just a static catalogue. It is a map of pathways through which matter can move under extreme conditions. Radioactive decay is one of the ways the universe edits its own elemental inventory over time, and still, the most striking thing, to me at least, is how quiet all this looks from the outside. A rock can contain unstable nuclei. A medical tracer can quietly emit radiation inside a hospital. Ancient minerals can record geological time through slow decay. The warmth inside Earth owes something to radioactive processes in heavy elements. The sun shines because nuclei in its core are constantly being transformed. None of these facts are visible in the ordinary surface appearance of things. The nucleus carries on its business beneath the threshold of everyday perception, and yet the consequences are everywhere. So when nuclei tremble, split, or decay, they are not stepping outside the normal story of matter. They are revealing what the normal story always contained. The nucleus is a bound but dynamic object. It can hold excess energy and then release it. It can adjust an unfavourable proton to neutron balance. It can tunnel through barriers. It can divide when its internal stresses become too great, or when a reaction nudges it into a more vulnerable state. Each of these transformations is a different answer to the same deep question. Given its structure, its composition, and the forces acting within it, what is the most favourable way for this nucleus to exist? Some answers are very long-lived. Some are brief. Some end in quiet gamma rays. Some in emitted particles. Some in dramatic division. But all of them belong to the same strange little world at the centre of the atom, where stability is never just stillness and change is never just destruction. A decaying nucleus is not a failure of matter. It is matter following its own logic toward a different arrangement. And once you see that clearly, another thought begins to press in from the edges of the story. These nuclei that tremble and transform are not isolated curiosities. They are the means by which the elements themselves have been shaped across cosmic history. The gold in a ring, the calcium in bone, the iron in blood, the uranium in old rock, none of these began as permanent givens. They were forged, altered, and sorted by nuclear processes in stars and stellar deaths long before they entered any world like ours. The nucleus, for all its tiny size, is also the author of matter on the grandest scale. And that makes the next turn in the story hard to resist, because once nuclei can change, the universe can build. Once you understand that nuclei can change, the universe itself begins to look different. Matter is no longer a set of permanent ingredients waiting passively to be arranged into stones, seas, trees, and living things. Matter has a history. The elements are not all original members of creation in equal standing. Some are ancient and abundant because they were easy for the young universe to make. Others required stars. Others required stars to die. Some demanded such violent conditions that for a long time the universe could not produce them at all. and that means the nucleus is not only the centre of the atom, it is also the mechanism by which the universe wrote its own inventory over time. This is one of the most satisfying shifts in all of physics, because it takes something terribly small and gives it cosmic consequence without any exaggeration at all. The nucleus in an atom is tiny beyond ordinary imagination, and yet the story of what nuclei can form, what nuclei can survive, and what nuclei can transform into is the story of why the universe contains hydrogen and helium in overwhelming abundance, why stars can shine for billions of years, why carbon exists at all, why rocky planets can form, why iron appears in blood and in meteorites and in the cores of worlds, and why gold, uranium and other heavy elements are rare, precious and difficult. The large-scale character of the universe depends on the small-scale logic of the nucleus. To appreciate that properly, it helps to go all the way back to the beginning, not to the beginning in a philosophical sense, but to the early hot universe, where matter itself was still being sorted out. In those first minutes after the Big Bang, conditions were extreme enough for the lightest nuclei to form. Protons and neutrons could combine into simple nuclei before the universe expanded and cooled too far, but that early period did not last very long, and the resulting nuclear products were correspondingly limited. The young universe produced mostly hydrogen, along with a substantial amount of helium and tiny traces of a few slightly heavier nuclei. That was enough to set the stage, but it was not enough to make a chemically rich cosmos. There was no early abundance of carbon, oxygen, silicon, calcium, iron, or anything like the full periodic table we now take for granted. That is an important point, because it means the universe did not begin with all the ingredients needed for planets and life ready-made. It began mostly simple. Light nuclei dominated, complexity had to wait for stars, and stars are, in a very real sense, giant nuclear engines. They are places where gravity gathers vast amounts of hydrogen and helium into dense, hot interiors, raising temperature and pressure until nuclei can begin to overcome their mutual resistance, often enough to fuse. This is the great long miracle of stellar life. Stars shine because nuclei change. They are not merely burning in the ordinary chemical sense, as if a star were some outrageous cosmic bonfire. Chemical burning would be pitifully inadequate for a star. The sun would not last anything like its current age on chemistry alone. A star shines because in its core, light nuclei are being transformed into more tightly bound ones, and the differences in binding energy emerge as released energy. In a star like the Sun, the process begins with hydrogen. Hydrogen nuclei are just single protons in their simplest form, and getting them to fuse is not easy. Positive charges repel one another, as we have discussed more than once, and in the calm daylight of ordinary experience, that repulsion is enough to keep them apart indefinitely. But the core of a star is not calm in any ordinary sense. It is hot, dense, and crowded enough that over immense numbers of collisions, rare successful encounters occur. Through a chain of reactions, hydrogen is gradually turned into helium. The helium nucleus is more tightly bound than the separate hydrogen nuclei that contributed to its making, and the difference becomes energy. That energy works its way outward from the core and eventually leaves the star as light and heat. So when sunlight reaches your skin or warms a wall or catches the edge of a window in late afternoon, what you're feeling is the delayed result of nuclei in the sun finding more favourable arrangements. The warmth is nuclear history in transit. It began in the centre of a star in the logic of binding energy, and spent a very long journey making its way outward. There is something immensely grounding in that. The light by which plants grow and weather moves and days begin is tied directly to the fact that the atomic nucleus can be changed. As stars age, the story grows richer. A star does not merely sit there converting hydrogen into helium forever. The nuclear fuel in its core gradually changes the conditions inside. When enough hydrogen has been transformed, the core evolves. In stars massive enough, new phases of fusion can begin. Helium nuclei can combine under the right conditions to make carbon, and from there, increasingly massive stars can continue through further stages, building oxygen, neon, magnesium, silicon, sulfur, and eventually nuclei in the region of iron. This sequence is not arbitrary. It follows the same binding logic that governs all nuclear processes. Each stage is possible only where the products are more tightly bound in the relevant way than the ingredients, and where the star can provide the conditions needed to force nuclei close enough together, often enough for reactions to proceed. Carbon is especially worth pausing over because it has a near mythic importance in the chemistry of life, and yet it is not something the early universe made in abundance. Stars had to produce it. Helium nuclei do not combine into carbon in a completely straightforward way. The process requires conditions and nuclear properties that are peculiarly favourable. If those properties were significantly different, the universe might contain far less carbon than it does, and the chemistry that makes life rich and flexible would look very different. This does not mean the universe was somehow aimed at us in any simple sense. It means that the detailed behaviour of nuclei has consequences that cascade upward into the possibilities of chemistry, geology, biology, and history. The nucleus is not a remote abstraction. It sets terms for what can exist later. Oxygen too is stellar work. So are many of the elements that make rocks and water and breathing bodies possible. The calcium in bone, the phosphorus in cells, the silicon in sand and stone, the sulfur in proteins, the iron in blood, these are not primitive leftovers from the beginning in their present abundance. They were made in stars or in the violent events that accompany stellar death. The material of life is reworked nuclear matter. You're not merely made of atoms. You're made of atoms whose nuclei were forged through a very long sequence of cosmic environments, each one capable of creating only certain possibilities. Iron marks an especially important turning point in this story. Nuclei around the iron region are among the most tightly bound. That means ordinary fusion in stars is no longer an easy downhill road beyond that point. For light nuclei, fusion releases energy because the products are more tightly bound. But once you are near the most tightly bound region, further fusion no longer gives the same energetic reward. In fact, trying to push significantly beyond that region through simple fusion can cost energy rather than release it. This places a limit on how stars live by fusion alone. Massive stars can build up layered interiors where progressively heavier elements are fused, but once iron-rich cores form, the star reaches a profound kind of crisis. The simple nuclear bargain that sustained the star for so long begins to fail, and when massive stars fail, they do so with remarkable consequences. A very massive star can end its life in gravitational collapse and explosion. The details are subtle and still actively studied in places, but the broad picture is one of the great transformations in astrophysics. The inner regions collapse under gravity once the available support is no longer sufficient. The resulting catastrophe can produce a supernova, an event of extraordinary violence and brightness. In those brief terrible moments, conditions arise that can drive nuclear processes far beyond the calm, steady fusion of ordinary stellar life. The explosion does not merely destroy, it creates. Nuclei that would not form easily in gentler conditions can be assembled, and existing nuclei can be reshaped by floods of energetic particles and intense environments. For a long time, supernovae were the leading dramatic image people invoked when talking about the creation of the heaviest elements, and with good reason. They are among the most energetic events in the universe, and they clearly play a major role in dispersing stellar products into space. When a star explodes, the material it has spent millions of years building is no longer locked away in its interior. It is thrown out into the interstellar medium, enriching the gas between stars with heavier nuclei. Future stars, planets, and living systems can then be built from that enriched material. This is why the universe changes chemically over time. Early generations of stars begin with simpler material. Later generations inherit the nuclear labour of those that came before. But in the last several decades, another site of heavy element production has become increasingly important in the story, and that is the collision of neutron stars. A neutron star is itself one of the strangest objects in nature, the collapsed remnant of a massive star, dense beyond ordinary tolerance, essentially a stellar corpse made largely of neutron-rich matter. When two neutron stars spiral together and merge, the conditions can be so extreme and so rich in neutrons that they become ideal for building some of the heaviest nuclei. These mergers can produce large amounts of heavy elements through rapid sequences of neutron capture followed by decay. In plain language, they offer a workshop for making nuclei that are simply too difficult for quieter environments. This matters because many of the very heavy elements around us, including some of the ones human beings have treasured most, likely owe a significant share of their existence to such extreme events. Gold is a favourite example because it combines scientific interest with human weakness in a particularly efficient way. The gold in jewellery, electronics and buried treasure chests did not come from ordinary stellar burning. It required far more intense nuclear circumstances. The same is true for many heavy elements beyond iron. Uranium too is part of this story. The nucleus that later became a source of geological heat, scientific insight and terrible weaponry was forged long before Earth existed, in environments violent enough to assemble it, and then scatter it into the gas from which later stars and planets formed. So when we say that the elements were forged in stars, that statement is broadly true, but also richer than it first sounds. Some were made in stars during their long ordinary lives, some were made in the explosive deaths of stars, some were made in collisions between exotic stellar remnants. The universe is not a single factory. It is a chain of foundries, each with its own specialty. Light elements come from the early universe and ordinary stellar burning. Many medium elements come from stellar interiors. The heaviest often require catastrophe. The periodic table is not just a list. It is a record of environments. And then comes the part that always deserves to be said plainly. Those nuclei did not remain where they were made. They were carried outward, mixed into gas and dust, incorporated into new stars and planetary systems, locked into minerals and oceans and atmospheres, taken up into chemistry, into biology, into bodies. The carbon in your tissues may once have been part of a red giant star. The oxygen you breathe was made in earlier generations of stars. The iron in your blood was forged in a stellar core and then scattered into space in a long-dead explosion. The calcium in your bones, the phosphorus in your cells, the potassium in your nerves, all of it comes from nuclear stories that began before the Earth formed. This idea is often reduced to a slogan about being made of star stuff, and while that slogan is not wrong, it can become so familiar that it loses force. The deeper statement is more precise and, to me, more impressive. You're made of nuclei whose existence depends on very specific episodes in cosmic history. Not all stars make carbon. Not all stellar deaths make uranium. Not all environments permit the same nuclear pathways. The matter in you is not just old, it is selective. It carries the outcome of different astrophysical conditions, layered together by gravity, chemistry, planetary formation, and evolution. The nucleus links your body to ancient stars not as a metaphor but as a material fact. The same is true for the Earth itself. Rocky planets require heavy elements. A universe made only of hydrogen and helium would not give you mountains, metal cores, continents, or the mineral richness that chemistry on planetary surfaces can exploit. The very existence of a world with silicon in its crust, iron in its centre, uranium in old rock, and enough carbon, oxygen and nitrogen near the surface to support life depends on multiple generations of nuclear processing across cosmic time. A planet is a late product of nuclear history. It is not merely matter gathered, it is matter enriched. There is also a kind of nuclear inheritance at work in the present day. The Earth is not just a cold museum of ancient nuclei. Some of the heat inside it still comes from radioactive decay of long-lived heavy elements. That internal heat helps drive geological activity. It contributes to mantle convection, volcanism, plate tectonics, and the restless shape of the world over immense timescales. So the same heavy nuclei forged in ancient violent astrophysical events continue to influence the behaviour of our planet now. Nuclear history did not end when the Earth formed. It is still unfolding beneath our feet. In living things, the carried through everything part of the story becomes almost intimate. Photosynthesis depends on sunlight from nuclear reactions in the sun. The molecules doing the work depend on elements forged in earlier stars. The metabolism of animals and plants depends on chemical structures built from nuclei that themselves were assembled in stellar interiors or explosions. The logic of the nucleus runs through the chain without ever being visible in an ordinary glance. A leaf does not look nuclear. Blood does not look nuclear. Sand does not look nuclear. But all of them rest on which nuclei exist, how stable they are, and where the universe was able to make them. Even technology follows this inheritance. The copper in wiring, the silicon in microchips, the rare elements used in certain specialized devices, the medical isotopes employed in diagnosis and treatment, the uranium used in reactors, the americium in some detectors, all of it traces back to the behavior of nuclei across vast stretches of time. Our machines and medicines are late cultural uses of ancient cosmic products. The nucleus is not merely inside the atom, it is inside civilization. What I find especially satisfying here is that the story does not become less personal as it becomes more cosmic. It becomes more personal. The closer one looks, the more ordinary life turns out to be threaded through with nuclear history. A glass of water contains oxygen nuclei made in stars. A piece of chalk carries calcium forged in ancient stellar processes. The air and soil, the minerals in teeth, the iron in a nail, the iodine in a body, all are examples of matter that has passed through nuclear foundries before ending up in seemingly local and familiar forms. The universe built these possibilities long before anyone could name them. And this is also why abundance matters. Hydrogen is everywhere because the early universe made it easily and in enormous quantity. Carbon and oxygen are common enough to shape chemistry and life because stars are able to make them in significant amounts. Gold is rare because the conditions needed to produce it are rarer. Uranium is rarer still in many contexts and unstable besides. The periodic table is not democratically distributed. The cosmos has preferences based on what its nuclear environments can actually supply. That is why some elements are so common that entire oceans, atmospheres and crusts depend on them, while others are treasured precisely because the universe does not hand them out generously. There is something almost geological in the way nuclear history accumulates. One generation of stars enriches the medium from which the next generation forms. Over time, galaxies become more chemically complex. Later stars are born with a higher fraction of heavier elements than very early stars had. Planet formation becomes correspondingly richer in possibilities. A world like Earth is not just placed anywhere in cosmic history without consequence. It arises in a universe that has already done enough nuclear work to make rocky chemistry, metal-rich interiors, and biologically useful elements available. In that sense, planets like ours are latecomers, beneficiaries of earlier stellar labour. And yet, for all that scale, the process still comes back to the same tiny core. Every one of these cosmic stories depends on the behaviour of nuclei, how strongly they bind, which reactions are allowed, which decays occur, which balances of protons and neutrons can survive. The furnace of a star is a story about nuclei. A supernova is a story about nuclei under extreme conditions. A neutron-star merger is a story about nuclei and nuclear matter in perhaps the harshest setting the universe commonly provides. The atom carries the cosmos in its centre, and the cosmos writes itself through the atom. So when we say forged in stars and carried through everything, we're not indulging in a grand phrase for its own sake. We're naming a literal truth. The material of daily life has passed through nuclear processes on scales ranging from the early universe to stellar cores to violent cosmic collisions. The nuclei in your body and in the room around you are old travellers. They were made, altered, and scattered long before they were assembled into anything familiar. They have been carried through gas clouds, stars, explosions, planets, oceans, rocks, and living cells. The ordinary world is full of matter with a violent ancestry and a calm present. And perhaps that is the right note to hold for a moment. The nucleus is tiny, but it is not a local matter. It reaches outward into astronomy, geology, chemistry, biology, and history. It explains why stars shine, why planets exist, why some elements are abundant and others scarce, why your body can be built from carbon and oxygen and calcium at all. The centre of the atom is also one of the places where the universe remembers what it has done, and once that becomes clear, there is really only one final question left to ask, which is what all of this makes the nucleus, not just physically, but in the larger sense of how we should think about it. After all the force, the tension, the binding, the decay, and the stellar forging, what secret is the nucleus actually keeping at the centre of the world? And once that becomes clear, the nucleus stops looking like a topic from a textbook and starts looking like one of the deepest organising facts in the universe. It is not merely a small object hidden inside the atom. It is the place where identity, stability, energy, and history are packed together so tightly that separating them no longer makes sense. That, I think, is the secret at the centre of the world. Not that the nucleus is mysterious because it is hard to see, though it certainly is. Not that it is important because it contains most of the atom's mass, though that matters too. The deeper secret is that so much of reality depends on something so small being arranged in exactly the difficult way it is. If you step back from everything we have followed, the shape of that secret begins to show itself. The nucleus is the reason atoms have distinct identities. Change the number of protons and you do not merely adjust the atom, you create a different element. The whole periodic table, with all the chemistry it allows, is rooted there. The nucleus is also the reason some atoms endure and others change. It sets the stage for stability, for radioactivity, for transmutation, for the slow heat inside planets and the light inside stars. It is the source of the energy that powers the sun, the reason heavy elements can exist at all, and the reason a world like ours can be made of more than hydrogen and helium. All of that begins in a place so small that ordinary imagination cannot hold it directly, only circle around it carefully. That alone would already be enough to make the nucleus remarkable, but the real force of it comes from how unlikely its existence seems when first described honestly. A nucleus is not a natural-looking thing in the way a stone or a cloud or a drop of water feels natural. It is a packed collection of particles held under conditions that seem almost designed to fail. The protons repel one another electrically. That repulsion does not politely disappear because a chemist would like matter to behave. It remains there, acting across the whole charged assembly. The strong nuclear force holds nucleons together, but only at very short range. The neutrons help by contributing to binding without adding electric repulsion, yet even that solution has limits. Large nuclei need careful balance. Heavy nuclei live under strain. Some decay, some split, some persist only because the numbers work out just well enough. The secret, then, is not that the nucleus exists in a simple or obvious way. The secret is that nature found a way to make such a difficult object real. And that is what I mean by saying the nucleus is an organising fact. It is not just a component of matter, it is a condition for the kind of matter the universe can have. If nuclei could not hold together, the world would remain chemically poor. If the strong force were weaker, or if the balances among nuclear states were different in the wrong ways, the periodic table might collapse into a very short and rather disappointing list. If carbon could not be formed in stars, then chemistry would lose one of its great flexible frameworks. If oxygen were far rarer, planets like Earth would be different beyond easy recognition. If heavy nuclei could not exist, then rocky worlds, geology, and the long stories of planetary evolution would be altered beyond measure. The center of the atom is one of the places where possibility itself gets edited. There is also something deeply satisfying in the way the nucleus brings together two things that often feel separate in everyday thought: the local and the cosmic. The local is the table, the glass, the skin, the air in a room, the iron in blood, the calcium in bone. The cosmic is stars, supernovae, neutron star mergers, the early universe, the long chemical evolution of galaxies. Normally we keep those scales apart. One belongs to daily life, the other to astronomy. But the nucleus refuses that separation. The nuclei around you are the local form of cosmic history. The room is full of atomic centers whose properties were set by forces that also determined what stars can do, what elements can be made, and what kinds of worlds can form. The closest things and the furthest things are tied together by the same nuclear rules. This is one reason I think the nucleus feels so intellectually powerful once it finally settles into view. It changes what counts as a deep explanation. Before you look closely, it is easy to think that explaining the visible world means talking about objects at the scale of experience: rocks, rivers, storms, organisms, machines. Those are the familiar actors, but once the nucleus enters properly, you begin to see that the world is not only built from smaller things, it is built from smaller things whose internal rules decide what larger things are possible. The nucleus does not tell you why one person becomes a painter and another an accountant, thankfully. But it does tell you why iron exists, why uranium decays, why the sun shines, why carbon-based chemistry is available, and why the materials of planets and bodies can be what they are. That is a very large jurisdiction for such a small domain. Another part of the secret is that the nucleus forces us to abandon the idea that solidity and permanence are simple. Matter feels solid. A chair does not suggest a balancing act among strong force, electric repulsion, shell structure, and binding energy. A wall gives no sign that its atoms contain tiny central systems full of old tensions and ancient history. The world appears calm because nuclear order is hidden beneath scales we do not sense directly. That hiddenness can make matter look simpler than it is. The nucleus corrects that impression. It tells us that apparent stillness is often the result of successful underlying organization, not the absence of difficulty. A stable nucleus is not simple because nothing is happening. It is simple only from far away. That lesson matters well beyond nuclear physics. It is one of those ideas that quietly reshapes how you look at reality in general. Stability is often not the same as ease. Endurance is often not the same as lack of pressure. The nucleus is a compact example of this. It endures not because its ingredients sit together naturally without conflict, but because the arrangement lowers the total energy enough, and the available barriers are high enough that the bound state persists. Some nuclei persist for the age of the universe, others decay quickly, but in every case, what looks like a settled object is the outcome of competing principles, not the absence of them. Nature often achieves order not by removing tension, but by structuring it. And perhaps that is why the nucleus feels so central in a philosophical sense as well as a physical one. It is one of the places where the universe shows most clearly that identity is relational. A proton on its own is one thing. A neutron on its own is another. Put them together in one configuration and you have one nucleus. Change the count and you have another. Bind them and the total mass changes. Alter the balance of protons and neutrons and the stability changes. Rearrange the structure and new decay paths appear. The whole is not just a pile of parts. The whole is defined by how the parts are related, and those relations are not decorative. They are the object. That may sound like a broad conclusion to draw from nuclear structure, but I do not think it is an exaggerated one. The nucleus is one of the clearest cases where nature insists that inventory is not enough. You cannot understand a nucleus by listing what is in it, and then stopping there. You need the arrangement, the forces, the energy accounting, the shell structure, the possible deformations, the barriers, the collective behavior, the decay channels. Only then does the object begin to come into focus. In that sense, the nucleus is not just a thing. It is an organised state of matter under very specific conditions. The secret at the centre of the world is that organisation goes deeper than appearance suggests. There is also a moral, if that is not too heavy a word for a scientific script, in how human beings came to know any of this. No one sees nuclei in the way we see rain, or wood, or birds crossing a field. They had to be inferred, measured, tested, challenged, and described through experiments so delicate and clever that they still feel a little miraculous. Scattering decay studies, mass measurements, reaction products, spectra, detector traces, each of these gave a piece of the story. The nucleus was not handed to human understanding ready-made. It had to be teased out of evidence, and that too is part of its secret. It reminds us that some of the most important things in reality are not obvious to the senses. They become visible only through disciplined imagination tied firmly to experiment. That is a lovely thought, I think, because it means the world is not only stranger than it first appears, but also more knowable than it first appears. The nucleus is hidden, yes. It is difficult, yes. It resists ordinary intuition almost at every turn, and still, human beings learned enough about it to explain radioactivity, to understand the source of stellar energy, to map the nuclear landscape, to build reactors, to make bombs, to use isotopes in medicine, to trace the ages of rocks and fossils, and to reconstruct the chemical history of stars and galaxies. There is a quiet triumph in that. We are creatures large enough to hold a teacup and small enough to be baffled by our own cupboards, yet also capable of discovering what binds the atomic nucleus and what stars do with it. Of course, that triumph has never been innocent. The nucleus gave us not only explanation but power, and power is never simple. Once people learned how much energy is tied up in nuclear binding, the path opened in more than one direction. On one side came medicine, imaging, cancer treatment, dating methods, deeper knowledge of geology and cosmology, and a clearer account of how the universe works. On the other side came the bomb, one of the starkest examples in history of intelligence outrunning wisdom. The nucleus is central not just scientifically but morally because it revealed a layer of reality from which enormous human consequences follow. It is one of those discoveries that made our species both more informed and more dangerous. That double legacy, I think, makes the nucleus feel even more like a true centre. It is not merely the centre of the atom, it is one of the centres of modern thought. Around it gather questions about what matter is, how stars live, where elements come from, how energy can be released, how time can be measured through decay, how the earth is heated from within, how medicine can see inside the body, how human beings can transform scientific knowledge into both healing and horror. Very few physical objects carry that range of consequence. The nucleus does. And yet, for all that grandeur and danger, it remains something almost absurdly small. I keep coming back to that, because scale is part of the wonder. The most consequential features of reality are not always grand in size. They are grand in what depends on them. The nucleus is tiny, but everything from the light of the sun to the composition of your bones depends on its behaviour. The ordinary world stands on an invisible architecture of bound nuclear matter. Chairs, oceans, teeth, mountains, rain, blood, starlight, metal tools, old rocks, all carry the signature of nuclear structure whether they know it or not, which they do not, and perhaps that is just as well. There is also a kind of quiet humour in the fact that the nucleus, despite being so foundational, is not in the least interested in being intuitive. One might hope that the centre of matter would be a reassuringly straightforward place. A neat ball of mass, perhaps, sitting politely at the centre of the atom and minding its own business. Instead, we get quantum shells, collective motion, residual strong force, binding energy, tunnelling, deformation, magic numbers, decay chains, and cosmic element factories. The nucleus behaves less like a tidy final answer and more like a compact committee of difficult truths. It is the sort of thing only the universe would consider an acceptable foundation for reality. But maybe that is exactly why it deserves the title we have given it. The secret at the centre of the world is not a single hidden sentence. It is a whole arrangement of facts that fit together more deeply than first impressions allow. The nucleus is the centre of the atom, yes, but also the centre of elemental identity. It is the meeting place of force and energy, of stability and change, of local structure and cosmic history. It is where the universe stores mass, tension, and possibility in one compact form. It is the reason atoms can be different from one another, the reason stars can build, the reason planets can be rich in material, the reason matter can have memory. Memory is an important word there. A nucleus carries memory in several ways. Its proton count remembers what element it is. Its neutron count remembers which isotope it is. Its binding energy remembers how strongly it is held together. Its stability or instability remembers the balance of forces available to it. Its very existence may remember ancient stellar events that made it possible. Some nuclei carry literal clocks in the form of decay probabilities, letting human beings read the ages of rocks, bones, and meteorites. Others carry the thermal legacy of planetary interiors. The nucleus is matter with a past folded inward, and because of that, it is also matter with a future. Nuclei can persist, decay, react, absorb, split, fuse, and transform. The centre is not dead. It is active according to its own rules. Stars continue to fuse nuclei. Radioactive isotopes continue to decay. Neutron stars continue to exist as laboratories of extreme nuclear matter. Human beings continue to use and misuse nuclear processes. The secret at the centre of the world is not something the universe finished long ago and placed under glass. It is ongoing. Every second, somewhere, nuclei are changing, and energy is being released because of the same logic we have been tracing all along. So what is a nucleus, really? At the start, that sounded like a question about a tiny object. Now it sounds more like a question about the structure of reality. A nucleus is a bound system of protons and neutrons held together by the strong interaction, despite the electrical repulsion of its protons. It is the source of elemental identity. It is the seat of most atomic mass. It is a quantum structure with shells, shapes, and collective behavior. It can be stable or unstable, quiet or radioactive, spherical or deformed, light enough to fuse in stars or heavy enough to split. It is tiny, but it is not small in consequence. And why should it fly apart? Because in one sense it always wants to. The protons always repel. The heaviest nuclei always strain against their own charge. Instability is never far away in the nuclear landscape. But why does it not? At least not always. Because binding wins often enough. Because the strong interaction is fierce where it needs to be. Because neutrons help without adding electrical burden. Because quantum structure creates favoured arrangements. Because lower energy states can be astonishingly resilient. The nucleus survives not by simplicity, but by successful balance. Perhaps that is the quietest and truest version of the secret. At the centre of the world is not a perfect, still little object. At the centre of the world is a balance, a difficult, powerful, precise balance out of which the richness of matter emerges. The visible world depends on a hidden settlement among forces, particles, and energy. Everything solid rests on something under tension. Everything ordinary rests on something extraordinary. And the next time you look at anything at all, a wall, a cup, a hand, a patch of sunlight, a stone, it may be worth remembering that beneath all its familiar surface lies that tiny compact centre, still doing its quiet work, holding history and possibility together in the dark.